the full history of the universe from the Big Bang to the end. Welcome to our journey through the history of the universe. In this video, we'll explore the grand narrative of everything from the birth of the cosmos to the evolution of stars and galaxies, right up to the present day. We'll unravel the mysteries that have fascinated humanity for centuries and delve into the scientific discoveries that have shaped our understanding of the universe. Get ready to embark on an epic adventure through time and space. To understand the universe, we must start with a definition. The universe encompasses all of space-time, matter, and energy. It's everything that exists, from the smallest subatomic particles to the vast expanse of galaxies. By studying the universe's history, we gain insight into the fundamental nature of reality and our place within it. This knowledge not only satisfies our curiosity, but also informs our understanding of how we came to be. The history of the universe is marked by a series of profound events that have shaped its current state. These events include the Big Bang, the formation of fundamental forces, the creation of matter, the birth of stars and galaxies, and much more. Each of these milestones represents a pivotal moment in the universe's evolution, leading to the complex and diverse cosmos we observe today. Understanding these events provides a framework for exploring the universe's history. Our journey begins with the Big Bang, the moment that marks the birth of the universe. The Big Bang theory posits that the universe began as an incredibly hot and dense point, approximately 13.8 billion years ago. This initial state set the stage for all subsequent cosmic evolution. The evidence supporting the Big Bang is compelling, including the cosmic microwave background, radiation, and the observed expansion of the universe. These observations have led scientists to develop a detailed understanding of the universe's earliest moments. In the aftermath of the Big Bang, the universe underwent a rapid expansion known as the inflationary period. During this brief but crucial phase, the universe expanded exponentially, smoothing out any initial irregularities and setting the stage for the formation of matter. This period was followed by the cooling and condensation of energy into the first particles. These particles, primarily quarks and gluons, formed the building blocks of matter as we know it. As the universe cooled further, the fundamental forces began to separate, initially unif, in the extreme conditions of the Big Bang. These forces differentiated into gravity electromagnetism, the weak nuclear force, and the strong nuclear force. Each force plays a crucial role in the structure and behavior of the universe. Gravity, for instance, governs the motion of celestial bodies, while electromagnetism is responsible for light and electromagnetic radiation. The weak and strong nuclear forces, meanwhile, dictate the interactions within atomic nuclei, with the fundamental forces established. The universe was primed for the creation of matter quarks combined to form protons and neutrons, which then merged to create atomic nuclei in a process known as nucleosynthesis. This period, occurring within the first few minutes of the universe's existence, resulted in the formation of hydrogen and helium, the simplest and most abundant elements. The matter-antimatter asymmetry observed in the universe today also emerged during this time, leading to a dominance of matter over antimatter. The next major milestone was the formation of the first atoms during the recombination era. As the universe continued to cool, protons and electrons combined to form neutral hydrogen atoms. This process allowed the universe to become transparent to light, giving rise to the cosmic microwave background radiation that we observe today. This radiation provides a snapshot of the universe at a crucial stage in its development, offering valuable clues about its early history. Following the recombination era, the universe entered a period of darkness before the first stars began to form. Gravitational collapse of gas clouds led to the birth of population. 3 stars, the first generation of stars, composed primarily of hydrogen and helium. These stars played a critical role in the risation of the universe and the formation of the first galaxies, supermassive black holes, likely formed from the remnants of these early stars, contributed to the growth and evolution of galaxies over time. As galaxies formed and evolved, they began to merge and interact, leading to the complex, large-scale structures we observe in the universe today. Galaxy clusters, superclusters, and vast cosmic voids emerged, creating a web-like structure that spans the cosmos. Dark matter, an invisible but essential component of the universe, has a significant influence on this large-scale structure. its gravitational effects help bind galaxies and clusters together, shaping the universe's overall architecture. Finally, our journey brings us to the formation of the solar system and the emergence of life on Earth. The solar system formed from the gravitational collapse of a molecular cloud, resulting in the birth of the Sun and the accretion of planets Earth, positioned within the habitable zone of the Sun, developed conditions suitable for life. Understanding the processes that led to the formation of our solar system and the emergence of life provides valuable context for our place in the universe and the potential for life elsewhere. The Big Bang marks the inception of our universe. This extraordinary event occurred approximately 13.8 billion years ago, transforming an extremely hot and dense point into the expansive cosmos we know today. Initially, the universe was an incredibly small and infinitely denser singularity. This singularity rapidly expanded, giving rise to all matter, energy, and the fundamental forces that govern our universe. The concept of the Big Bang is supported by substantial evidence observations, such as the cosmic microwave background radiation and the red shift of distant galaxies, provide crucial insights into this monumental event. The cosmic microwave background radiation is a faint glow permeating the universe. It represents the residual heat from the Big Bang, offering a snapshot of the universe when it was just 380,000 years old. Edwin Hubble's observations of distant galaxies revealed that they are moving away from us. This red shift effect suggests that the universe is expanding, a key prediction of the Big Bang theory. During the first moments of the Big Bang, the universe was incredibly hot and dense. This primordial state set the stage for the formation of fundamental particles and forces. In the aftermath of the initial expansion, the universe underwent a phase of rapid inflation. This exponential growth smoothed out irregularities and laid the foundation for the large-scale structure of the cosmos as the universe continued to expand. And cool quarks and gluons emerged. These subatomic particles are the building blocks of protons and neutrons, which later formed atomic nuclei. The early universe was a seething plasma of particles and energy. Over time, it cooled enough for quarks to combine, leading to the creation of protons and neutrons. The Big Bang also marks the beginning of time. As we understand it before this event, the concepts of time and space, as we know them, did not exist. The conditions during the Big Bang were extreme, with temperatures reaching unimaginable levels. These high temperatures facilitated the formation of the universe's first particles. As the universe expanded, it cooled rapidly. This cooling allowed for the formation of simple atomic nuclei, setting the stage for the creation of more complex matter. The evidence for the Big Bang continued to grow with advancements in technology and observations. Each new discovery helps refine our understanding of this pivotal moment in cosmic history. The Big Bang Theory not only explains the origin of the universe, but also its ongoing expansion. This expansion is a fundamental aspect of our evolving cosmos. Understanding the Big Bang is crucial for comprehending the universe's past, present, and future. It provides a framework for studying the cosmos and our place within it. The story of the Big Bang is a story of beginnings. It marks the start of an extraordinary journey that has led to the formation of stars, galaxies, and ultimately life on Earth. The evidence supporting the Big Bang Theory is both extensive and compelling. One of the most significant pieces of evidence is the cosmic microwave background radiation. This faint glow fills the universe and represents the residual heat from the Big Bang, discovered in 1965 by Arap Pennis and Robert Wilson. The cosmic microwave background radiation is a cornerstone of Big Bang cosmology. It provides a snapshot of the universe when it was just 380,000 years old, showing a remarkably uniform temperature with slight fluctuations. Another key piece of evidence is the observed expansion of the universe. Edwin Hubble's observations in the 1920s revealed that distant galaxies are moving away from us, indicating that the universe is expanding. Hubble's discovery of the redshift phenomenon in the light from these galaxies supports the idea that the universe began from a single point and has been expanding ever since this red shift occurs. Because light stretches as it travels through an expanding universe, shifting toward the red end of the spectrum. The abundance of light elements, such as hydrogen and helium, also supports the Big Bang Theory. These elements were formed during the first few minutes of the universe in a process known as nucleosynthesis. The predicted and observed ratios of these light elements match almost perfectly, providing strong evidence for the conditions present in the early universe. This agreement between theory and observation is a powerful confirmation of the Big Bang. Another line of evidence comes from the large-scale structure of the universe. The distribution of galaxies and galaxy clusters forms a cosmic web that aligns with predictions from the Big Bang model. Computer simulations of the universe's evolution from the Big Bang to the present day reproduce large-scale structures, further validating the theory. These simulations incorporate the effects of dark matter and dark energy, essential components of our universe. Observations of the cosmic microwave background radiation have revealed tiny fluctuations in temperature. These fluctuations correspond to density variations in the early universe that eventually led to the formation of galaxies and other structures. The precise measurements of these fluctuations by satellites like Cobb WMAP and Planck have provided detailed insights into the universe's age composition and rate of expansion. These measurements are consistent with predictions made by the Big Bang theory, the discovery of cosmic inflation, a rapid expansion of the universe in its earliest moments, also supports the Big Bang. This concept explains the uniformity of the cosmic microwave background radiation and the distribution of galaxies. Evidence for inflation includes the uniformity and slight irregularities in the cosmic microwave background. These features suggest a period of exponential growth that smoothed out the early universe's initial conditions. The Big Bang theory also explains the formation of the first atoms as the universe cooled protons and electrons combined to form hydrogen atoms, a process that left an imprint on the cosmic microwave background radiation. Further support comes from the study of distant supernova observations of these exploding stars have shown that the universe's expansion is accelerating, a phenomenon consistent with the Big Bang model. The discovery of dark energy, an unknown force driving this acceleration, has further bolstered the Big Bang theory. It fits within the framework of an expanding universe that began with a tremendous explosion. Overall, the convergence of multiple lines of evidence from different fields of astron and physics makes the Big Bang the most robust and widely accepted explanation for the origin and evolution of the universe. The initial conditions of the universe were extreme and unlike anything we experience today. Immediately following the Big Bang, the universe was a hot, dense plasma of particles. Temperatures were unimaginably high, and all four fundamental forces were unified in these first fractions of a second. The universe expanded exponentially during a period known as inflation. This rapid expansion smoothed out any irregularities and set the stage for the universe's large-scale structure. As inflation ended, the universe cooled and began to stabilize. During the first micros, seconds, quarks and gluons emerged from the energy of the Big Bang. These elementary particles are the building blocks of protons and neutrons. At this stage, the universe was still too hot for these particles to form stable nuclei. As the universe continued to expand and cool, it reached a point where quarks could combine to form protons and neutrons. This process marked the beginning of the formation of matter. As we know it, the universe was still a seething, opaque plasma of particles and radiation. Approximately 1 second after the Big Bang, the temperature dropped enough for neutrinos to decouple from matter. These elusive particles began to travel freely through the universe. Around the same time, protons and neutrons started to undergo nuclear reactions, leading to the synthesis of light elements. This period of nucleosynthesis lasted for about 3 minutes. During this time, protons and neutrons combined to form the nuclei of hydrogen, helium, and small amounts of lithium and barium. These light elements became the building blocks for future stars and galaxies. After nuclear synthesis, the universe continued to cool and expand. The high-energy radiation began to lose its intensity, and the universe entered a phase dominated by radiation. Matter and radiation were still tightly coupled, creating a dense, hot environment around 380,000 years after the Big Bang. The universe had cooled sufficiently for electrons to combine with protons, forming neutral hydrogen atoms. This recombination error allowed photons to travel freely, leading to the emission of the cosmic microwave background radiation. the universe became transparent. First time, the formation of neutral atoms was a crucial turning point. It marked the transition from an opaque plasma to a transparent universe, enabling light to travel vast distances. This transparency is what allows us to observe the cosmic microwave background radiation today. As the universe continued to expand, small density fluctuations began to grow under the influence of gravity. These fluctuations eventually led to the formation of large-scale structures such as galaxies and clusters. Dark matter played a significant role in this process, providing the necessary gravitational pull in the following millions of years. The first stars began to form from clouds of hydrogen and helium. These early stars, known as population 3 stars, were massive and short-lived. They contributed to the reionization of the universe, making it transparent to ultraviolet light. The intense radiation from the first stars initiated the rosation process, which lasted for hundreds of millions of years. During this time, the universe transitioned from being mostly neutral to mostly ionized. This epoch paved the way for the formation of galaxies and more complex structures. Galaxies began to form from gravitationally bound regions of dark matter and gas. The first galaxies were small and irregular, merging over time to create larger, more structured systems. Supermassive black holes likely formed in the centers of these early galaxies, influencing their evolution. The interaction and merger of galaxies led to the diverse range of galaxy types we see today, from spiral galaxies like the Milky Way to massive elliptical galaxies. These structures evolved through complex gravitational interactions. The large-scale structure of the universe became increasingly intricate throughout this period. The universe continued to expand, driven by dark energy. This mystery ooze force accelerates the expansion, shaping the future of the cosmos. Understanding the eye conditions and subsequent evolution of the universe helps us comprehend the vast dynamic universe we inhabit today. The inflationary period was a brief but critical phase in the early universe. It occurred just fractions of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion smoothed out any initial irregularities during inflation. The universe grew from subatomic scales to macroscopic sizes almost instantaneously. This expansion was driven by a high-energy field, often referred to as the inflaton field. The energy from this field caused space itself to stretch at an incredible rate. Inflation solved several key problems in cosmology, including the horizon and flatness problems. The horizon problem relates to the uniformity of the cosmic microwave background radiation. Inflation explains how distant regions of the universe could have the same temperature despite being too far apart to have exchanged information. The flatness problem concerns that the universe's geometry. Inflation drove the universe toward a flat Euclidean geometry, which aligns with current observations. This period set the initial conditions for the universe's subsequent evolution. As inflation ended, the energy driving the expansion was transferred into particles and radiation. This process, known as reheating, filled the universe with a hot, dense plasma. The end of inflation marked the beginning of the more gradual expansion that has continued to the present day. The rapid expansion during inflation also stretched quantum fluctuations to macroscopic scales. These fluctuations became the seeds for the large-scale structures we observe in the universe today. They are evident in the slight temperature variations in the cosmic microwave background radiation. Inflation theory predicts a nearly uniform but slightly perturbed distribution of matter and energy. These perturbations eventually led to the formation of galaxies, clusters, and other cosmic structures. The initial tiny fluctuations grew over time under the influence of gravity. The detailed measurements of the cosmic microwave background radiation by satellites such as Cobb WMAP and Planck provide strong evidence for inflation. These observations match the predicted patterns of temperature fluctuations. The data supports the idea that inflation played a crucial role in shaping the early universe. Inflation also provides a mechanism for the creation of the universe's large-scale structure by stretching space-time. Inflation amplified tiny quantum fluctuations into cosmic scale variations. This process set the stage for the hierarchical formation of galaxies and clusters. The concept of inflation is still an active area of research in cosmology. Scientists are working to understand the exact nature of the inflat field and the precise dynamics of the inflationary period. Despite these uncertainties, the basic framework of inflation is well supported by observational evidence. Inflation's implications extend beyond the formation of structure. It also offers insights into the fundamental nature of space-time and the early conditions of the universe. The period of rapid expansion highlights the dynamic and interconnected nature of the cosmos. The success of inflation in explaining key features of the universe makes it a central component of modern cosmological theories. It bridges the gap between the initial singularity of the Big Bang and the subsequent formation of matter and structure. This period is a cornerstone in our understanding of cosmic history. By solving long-standing puzzles in cosmology, inflation provides a coherent and predictive framework. It connects the quantum realm with the macroscopic universe, offering a unified picture of the cosmos's origin and evolution. This period underscores the profound interplay between fundamental physics and cosmology. The study of inflation continues to inspire new theoretical development and observational strategies as technology advances. Future observations may further refine our understanding of this pivotal array. The inflationary period remains a testament to the power of scientific inquiry in unraveling the mysteries of the universe. As the universe continued to cool after the inflationary period, the first particles began to form. Initially, the universe was a hot, dense plasma of quarks and gluons. These elementary particles are the fundamental building blocks of matter in the first microscope. After the Big Bang, quarks combined to form protons and neutrons. These particles are known as barons, and they are the primary components of atomic nuclei. The strong nuclear force played a crucial role in binding quarks together. As protons and neutrons emerged, the universe was still too hot for these particles to form stable nuclei. The high-energy environment caused constant collisions, breaking apart any net atomic structures. It wasn't until the universe cooled further that stable nuclei could form. During this cooling phase, electrons and neutrinos also formed. Electrons are lightweight, negatively charged particles that would eventually orbit atomic nuclei. Neutrinos are nearly massless particles that interact very weakly other matter, protons and neutrons, began to combine to form the first light nuclei in a process known as nucleosynthesis. This period lasted for about 3 minutes and results in the formation of hydrogen helium and small amounts of lithium and barium. These light elements were the first stable forms of matter. The formation of these light elements marked the end of the universe's particle formation phase. The universe transitioned from a quark-gluon plasma to a mix of light nuclei and free electrons. This set the stage for the formation of neutral atoms later on. As the universe expanded, the density and temperature continued to decrease. This allowed the light nuclei to survive without being disrupted by high-energy collisions. The universe was gradually becoming less hostile to the formation of more complex structures. The formation of the first particles was a critical step in the evolution of the universe. It provided the basic building blocks for all matter that would follow. The processes that governed this phase were driven by the fundamental forces of nature. The strong nuclear force was essential in holding quarks together within protons and neutrons. Without this force, the form of atomic nuclei would not have been possible. This force is one of the 4 fundamental interactions that shape our universe. The weak nuclear force also played a role in particle formation. It is responsible for processes such as beta decay, which changes neutrons into protons and vice versa. This force contributed to the balance of particles during the early moments of the universe. Electromagnetic interactions became increasingly important as the universe cooled. These interaction action govern the behavior of charged particles like electrons and protons. They are responsible for the formation of atoms and the emission and absorption of light. Gravity, the weakest but most far-reaching force, began to influence the large-scale structure of the universe. It caused regions of higher density to attract more matter, leading to the eventual formation of galaxies and stars. Gravity's influence grew as the universe expanded. The early universe was a dynamic and rapidly changing environment. The formation of the first particles was just the beginning of a long and complex process of cosmic evolution. This phase set the foundation for everything that would come later. Understanding the formation of the first particles helps us grasp the fundamental nature of matter It reveals the processes that shaped the universe's initial conditions and guided its subsequent development. This knowledge is crucial for piecing together the history of the cosmos. After the Big Bang, the universe was governed by a single unified force. As it expanded and cooled, this force began to separate into the four fundamental forces we observe today. This separation occurred in distinct phases during the early moments of the universe. The first force to separate was gravity. As the universe cooled to below the Planck temperature, gravity split from the other forces. This allowed it to begin shaping the large-scale structure of the cosmos. Next, the strong nuclear force separated from the electro-weak force. This occurred as the universe continued to cool, allowing quarks to bind together into protons and neutrons. The strong force is crucial for holding atomic nuclei together. Following this, the electro-weak force split into the electromagnetic force and the weak nuclear force. This separation defined the interactions that govern most of the phenomena we observe in the universe today. Electromagnetism controls light and atomic interactions, while the weak force is responsible for radioactive decay. Gravity, despite being the weakest of the four forces, plays a dominant role on cosmic scales. It governs the motion of planets, stars, and galaxies, and dictates the overall structure of the universe. The effects of gravity become more pronounced as structures form and grow. The strong nuclear force is the most powerful of the fundamental forces. It binds quarks together to form protons and neutrons and holds these particles within atomic nuclei. This force operates at very short ranges, but its effects are incredibly strong. Electromagnetism is the force responsible for interactions between charged particles. It governs the behavior of electrons in atoms and the emission and absorption of light. Electromagnetic forces are responsible for a wide range of physical phenomena, from electricity to magnetism to chemical bonding. The weak nuclear force is responsible for certain types of particle interactions, such as beta decay. This force plays a crucial role in the processes that power the sun and other stars. It operates at very short distances and is weaker than both the strong force and electromagnetism. The separation of these forces set the stage for the complex interactions that drive the universe's evolution. Each force has distinct properties and operates over different ranges, but together they govern the behavior of all matter and energy. The unification and subsequent separation of these forces is a central concept in particle physics theories that attempt to describe these processes are known as grand unified theories and seek to explain the behavior of the universe at its most fundamental level. The separation of forces also has profound implications for our understanding of the early universe. It helps explain the conditions that allowed for the formation of particles, atoms, and eventually the large-scale structures we observe today. Research into the separation of forces continues to be a major focus in physics. Scientists use particle accelerators to recreate the high energy conditions of the early universe, seeking to understand how these forces behave at fundamental levels. These experiments provide insights into the origins and nature of the universe. The concept of symmetry breaking is key to understanding the separation of forces. As the universe cooled, symmetrical states broke, leading to the distinct forces we observe today. This process is a cornerstone of modern physics, influencing theories from particle physics to cosmology. Understanding the separation of forces enhances our comprehension of the universe's early moments. It reveals the fundamental interactions that shape the cosmos, guiding the formation of matter and the evolution of structure. This knowledge is essential for constructing a complete picture of the universe's history. Gravity, though the weakest of the four fundamental forces, plays a pivotal role in shaping the universe. It governs the motion of planets, stars, and galaxies, and influences the formation of cosmic structures. Gravity's reach extends over vast distances, affecting objects across the entire cosmos. In the early universe, gravity began to draw matter together. Regions of slightly higher density attracted more matter, leading to the formation of gas clouds. These clouds eventually collapsed under their own gravity, forming stars and galaxies. Stars are born from the gravitational collapse of gas clouds. As these clouds condense, they heat up, eventually igniting nuclear fusion in their cause. Gravity continues to play a crucial role throughout a star's life, balancing the outward pressure from fusion. Gravity also governs the orbits of planets around stars in our solar system. The sun's gravity keeps the planet's coalesce in stable orbits, allowing life to thrive on Earth. This gravitational pull ensures that planets do not drift off into space in galaxies. Gravity binds stars together in a cohesive structure. It creates the spiral arms seen in many galaxies, including our own Milky Way. Gravity also influences the movement of stars within galaxies, dictating their orbits around the galactic center. Gravity is responsible for the formation of galaxy clusters. These clusters are groups of galaxies held together by their mutual gravitational attraction. Within these clusters, galaxies interact and merge, shaping their evolution over time. Supermassive black holes found at the centers of most galaxies are another manifestation of gravity's power. These black holes have masses millions to billions of times that of our sun. Their intense gravitational fields influence the motion of stars and gas in their vicinity. On even larger scales, gravity shapes the cosmic web. This web is a vast network of galaxies and dark matter connected by filaments stretching across the universe. Gravity pulls matter into these filaments, forming the large-scale structure of the cosmos. Dark matter, an invisible substance that makes up most of the universe's mass, interacts with gravity. Although we cannot see dark matter directly, its gravitational effects are evident in the rotation of galaxies and the distribution of galaxy clusters. Gravity also plays a role in the life cycle of stars. When a star exhausts its nuclear fuel, gravity causes it to collapse. This collapse can lead to the formation of dense objects like white dwarfs, neutron stars, or black holes. Depending on the star's initial mass, gravitational waves are ripples in space-time caused by accelerating massive objects like merging black holes or neutron stars. These waves carry information about the events that created them, providing a new way to observe the universe. Einstein's theory of general relativity revolutionized our understanding of gravity. It describes gravity not as a force, but as the curvature of space-time caused by mass and energy. This theory has been confirmed by numerous observations and experiments. Gravitational lensing occurs when a massive object like a galaxy or black hole bends light from objects behind it. This effect can magnify and distort the images of distant galaxies, allowing us to see objects that would otherwise be too faint gravity influences the expansion of the universe, while dark energy drives the acceleration expansion gravity works to slow it down. The interplay between these two forces determines the universe's fate. Overall, gravity's influence pervades every aspect of the cosmos, from the smallest particles to the largest structures. Gravity shapes the universe's evolution. Understanding gravity helps us unravel the complex interactions that define our universe. Electromagnetism is one of the four fundamental forces and plays a crucial role in shaping the universe. It governs the interactions between charged particles and is responsible for both electric and magnetic fields. This force is much stronger than gravity and operates over much smaller distances. Light, or electromagnetic radiation, is a key manifestation of electromagnetism. It travels in waves and carries energy across the cosmos. The spectrum of electromagnetic radiation includes visible light, radio waves, X-rays, and gamma rays. Photons are the particles of light, and they mediate electromagnetic interactions. These massless particles travel at the speed of light and are emitted and absorbed by charged particles. This interaction is what allows us to see and detect radiation. Electromagnetic waves are generated by the acceleration of charged particles. For example, electrons moving in antennas produce radio waves. In stars, nuclear reactions generate light that radiates into space. Electromagnetic force is responsible for the structure of atoms. Electrons are held in orbit around atomic nuclei by the attraction between their negative charge and the positive charge of protons. This force creates the stability necessary for the formation of matter, in addition to holding atoms together. Electromagnetism governs the bonding between atoms to form molecules. Chemical reactions result from the rearrangement of electrons in atoms driven by electromagnetic interactions. This is fundamental to chemistry and biology. Electromagnetic waves travel through space and can interact with matter in various ways. They can be absorbed, reflected, refracted, or scattered, depending on the properties of the material they encounter. These interactions are central to our understanding of optics and communication technologies. Light from distant stars and galaxies provides a wealth of information about the universe by analyzing the spectrum of this light. Scientists can determine the composition, temperature, and movement of celestial objects. This process is known as spectroscopy, the cosmic microwave background radiation, a relic of the Big Bang, is a form of electromagnetic radiation. It provides a snapshot of the universe when it was just 380,000 years old, revealing details about its early conditions and subsequent evolution. Magnetic fields generated by electric currents influence the behavior of charged particles. The Earth's magnetic field protects us from cosmic radiation and helps guide migratory animals. Magnetic fields are also crucial in the operation of many electronic devices. Electromagnetic forces are responsible for the emission of radiation from hot objects. This thermal radiation, including infrared and visible light, allows us to observe the temperatures of stars and planets. Infrared astronomy, for instance, reveals details about cooler objects in space. Electromagnetic interactions enable the detection of astronomical phenomena that are otherwise invisible. For example, radio telescopes capture radio waves emitted by distant galaxies, and nebula X-ray observatories reveal high-energy processes around black holes and neutron stars. The study of electromagnetism has led to profound discoveries in physics. Maxwell's equations, which describe how electric and magnetic fields interact, are fundamental to understanding light and electromagnetic waves. These equations unify electricity, magnetism, and optics. Overall, electromagnetism is essential to the functioning of the universe, and our understanding of it from the atomic to the cosmic scale. This force governs a wide range of phenomena. Its study continues to drive scientific and technological advancements. The weak nuclear force is one of the 4 fundamental forces in the universe. It is responsible for processes like beta decay, where a neutron transforms into a proton, an electron, and an antineutrino. This force plays a crucial role in the life cycle of stars. Unlike the strong nuclear force, the weak force operates over a very short range, even shorter than the diameter of a proton. It is much weaker than the strong nuclear force and electromagnetism, but stronger than gravity. Its effects are not as immediately apparent in everyday life. The weak nuclear force is essential in the fusion reactions that power the sun and other stars. These reactions convert hydrogen into helium, releasing enormous amounts of energy in the process. This energy is what provides the light and heat we receive from the sun in beta decay. The weak force changes the flavor of quarks, the fundamental particles that make up protons and neutrons. This process alters the identity of particles, transforming neutrons into protons, and vice versa. It is a key mechanism in the stability of atomic nuclei. The weak force is mediated by three massive gauge bosons: the W plus W and Z bosons. These particles are much heavier than protons or neutrons, which is why the weak force has such a short range. The exchange of these bosons between particles facilitates weak interactions. In addition to its role in nuclear processes, the weak force is crucial in the early universe. It helped govern the interactions that led to the matter-antimatter asymmetry we observe today. Without this asymmetry, the universe would have been a very different place. Neutrinos, nearly massless particles that interact only via the weak force and gravity, are produced in vast quantities in nuclear reactions. They pass through matter almost undisturbed, making them challenging to detect. Studying neutrinos helps scientists understand the weak force and cosmic phenomena. The weak nuclear force also has implications for particle physics and cosmology. Experiments in particle accelerators, such as those conducted at CERN, probe the properties of the weak force. These experiments have led to significant discoveries about the fundamental nature of matter-weak interactions, are also responsible for certain types of particle decays observed in cosmic rays and other high-energy processes. Understanding these interactions helps scientists piece together the puzzle of how particles behave under extreme conditions. The weak force plays a role in the synthesis of elements in stars during the late stages of stellar evolution. Weak interactions help create heavier elements. These elements are then dispersed into space when stars explode as supernovae, contributing to the cosmic abundance of elements. One of the key successes of the standard model of particle physics is its unification of the electromagnetic and weak forces into the electro-weak force. This theoretical framework describes how these two forces merge at high energies, providing a deeper understanding of their relationship. Research into the weak force continues to reveal new insights into the universe. Experiments with neutrino detectors and particle colliders push the boundaries of our knowledge. These studies aim to answer fundamental questions about the nature of matter and the forces that govern it. The weak force also has implications for understanding dark matter, the mysterious substance that makes up most of the universe's mass. Some theories suggest that dark matter particles interact via the weak force, making its study relevant to uncovering the nature of dark matter. In addition to its scientific significance, the weak force has practical applications. Understanding weak interactio NS is important for fields such as nuclear medicine and energy technologies that rely on nuclear reactions, like certain types of imaging and treatment, benefit from this knowledge. Overall, the weak nuclear force is a fundamental aspect of the universe's structure and behavior. It influences processes from the smallest scales of particle interactions to the largest scales of cosmic evolution. Its study continues to be a vital part of modern physics. The strong nuclear force is the most powerful of the four fundamental forces. It acts between quarks, binding them together to form protons and neutrons. His force is crucial for holding atomic nuclei together. Despite the repulsive electromagnetic force between positively charged protons operating over very short distances, the strong nuclear force is effective only within the atomic nucleus. It overcomes the electromagnetic repulsion between protons, ensuring the stability of most atomic nuclei. Without it, atomic nuclei would not exist. Gluons are the mediator particles of the strong nuclear force. They are massless and act as the exchange particles between quarks. The interactions between gluons and quarks are what bind quarks into protons, neutrons, and other hadrons. The strong force exhibits a property known as confinement. This means quarks cannot be isolated. They are always found in groups bound together by gluons. If you try to separate quarks, the force increases, creating more quark-antiquark pairs inside protons and neutrons. Quarks are constantly interacting through the exchange of gluons. These interactions are incredibly strong, making the binding energy of the nucleus very high. This high energy is released in nuclear reactions such as fusion and fission. Nuclear fusion, which powers the sun, relies on the strong force to combine hydrogen nuclei into helium, releasing vast amounts of energy. This process is the source of energy for stars and has potential applications in future energy production on Earth in nuclear fission. The strong force binds are broken when heavy nuclei like uranium split into smaller nuclei. This process also releases a significant amount of energy, which is harnessed in nuclear power plants and weapons. The strong nuclear force is described by the theory of quantum chromodynamics, or QCD. QCD explains how quarks and gluons interact through the strong force. It is a fundamental part of the standard model of particle physics. Music, the behavior of the strong force at different energy scales, is a subject of ongoing research at high energies, such as those achieved in particle accelerator. The strong force behaves differently than at lower energies, leading to phenomena like asymptotic freedom. Asymptotic freedom means that at extremely high energies, quarks interact less strongly, behaving almost as free particles. This counterintuitive property has been confirmed through experiments and is a key feature of QCD. The strong nuclear force also plays a role in the formation of exotic states of matter in extreme conditions such as those found in neutron stars or created in particle colliders. Quarks and gluons can form a quark-gluon plasma, a state of matter that existed shortly after the Big Bang. Studying the strong force and quark glue and plasma helps scientists understand the early universe's conditions. High energy physics experiments, such as those conducted at sea, aim to recreate and study these extreme states of matter. The strength of the strong nuclear force is responsible for the stability of elements in the periodic table. Elements with stable nuclei owe their existence to the balance between He strong force and the electromagnetic force. This balance determines the variety of elements found in nature. Understanding the strong nuclear force provides insights into the fundamental structure of matter. It explains why atomic nuclei are stable, how elements are formed, and the behavior of matter under extreme conditions. The study of this force continues to be a central focus in both theoretical and experimental physics. Quarks are fundamental particles that combine to form protons and neutrons. They come in 6 different types, known as flavors: up, down, charm, strange, top, and bottom. These flavors combine in various ways to create different particles. Gluons are the particles that mediate the strong nuclear force between quarks. They are massless and carry the force that holds quarks together. Inside protons, neutrons, and other hadrons, gluons themselves interact with each other, making the strong force unique among the fundamental forces. Each proton and neutron is made up of 3 quarks bound together by gluons. A proton consists of 2 up quarks and 1 down quark, while a neutron is made up of 2 down quarks and 1 up quark. The gluons constantly exchange between quarks, maintaining the strong force that binds them. Quarks possess a property called color charge, which comes in 3 types: red, green, and blue. Gluons carry a combination of these color charges, facilitating the interaction between quarks. The exchange of gluons ensures that quarks remain confined within hadrons. Quarks are never found in isolation due to a phenomenon known as confinement. The strong force becomes stronger as quarks move apart, eventually creating new quark-antiquark pairs, rather than allowing a single quark to escape. This results in quarks always being bound within larger particles. The interactions between quarks and gluons are described by quantum chromodynamic, or QCD. QCD is a fundamental theory and particle physics that explains how the strong force operates. It is a complex and rich field of study, revealing much about the nature of matter. In addition to protons and neutrons, quarks combine to form other particles known as mesons. Mesons consist of a quark and an antiquark pair. They play a role in mediating the strong force between nucleons in an atomic nucleus. The study of quarks and louns has led to the discovery of many different particles. These particles, known as hadrons, include not only protons and neutrons, but also a variety of other combinations. Particle accelerators like those at CERN have been crucial in discovering and studying these particles. The behavior of quarks and gluons at high energies, such as those achieved in particle collisions, can reveal new insights into the early universe. when quarks and gluons are in a high energy state, they can form a quark-gluon plasma, a state of matter that existed just after the Big Bang. Quark-gluon plasma behaves differently from ordinary matter. It is a nearly perfect fluid with very low viscosity, allowing quarks and gluons to move free. Studying this state of matter helps scientists understand the conditions of the early universe and the fundamental properties of strong interactions. Experiments with quark-gluon plasma provide important data for testing theories of QCD. These experiments recreate conditions similar to those that occurred microseconds after the Big Bang, offering a window into the behavior of matter under extreme conditions. The properties of quarks and gluons are fundamental to the structure of matter. Understanding these particles and their interactions helps explain the stability of atomic nuclei, the formation of elements, and the forces that govern the universe at the smallest scales. Research into quarks and gluons continues to be a dynamic field in physics. Advances in experimental techniques and theoretical models are constantly improving our understanding of these fundamental particles. This research has broad implications for both basic science and potential applications. The knowledge gained from studying quarks and gluons contributes to our broader understanding of the universe. It connects the behavior of the smallest particles with the largest cosmic structures, revealing the intricate and interconnected nature of all matter. Overall, quarks and gluons are essential components of the universe's fundamental makeup. Their interactions, governed by the strong nuclear force, shaped the structure of matter and the forces that hold it together. This ongoing research continues to uncover the deepest secrets of the cosmos. As the universe cooled after the Big Bang, quarks began to combine, forming protons and neutrons. This process occurred during the first microsc of the universe's existence. The strong nuclear force played a crucial role in binding quarks together. Protons are composed of 2 p quarks and 1 down quark. Neutrons consist of 2 down quarks and 1 up quark. The exchange of gluons between these quarks holds them tightly together within the particles. The formation of protons and neutrons was a key step in the evolution of the early universe. These particles are the building blocks of atomic nuclei. Without them, the complex structures of matter would not exist, the strong nuclear force mediated by gluon is what makes protons and neutrons stable. It overcomes the repulsive electromagnetic force between the positively charged protons, allowing atomic nuclei to form during the first few minutes after the Big Bang. The universe was hot and dense enough for nuclear reactions to occur. Protons and neutrons collided and fused, forming the nuclei of the lightest elements. This period is known as Big Bang nucleosynthesis. In Big Bang nuclear synthesis, protons and neutrons combined to form helium, a heavy isotope of hydrogen nuclei, then fused to create helium-3, helium-4, and small amounts of lithium and beryllium. These reactions happened very quickly as the universe continued to expand and cool. The ratio of protons to neutrons during nucleosynthesis was crucial for the resultant abundance of elements. At high temperatures, neutrons could decay into protons, electrons, and neutrinos. As the universe cooled, this decay slowed, leaving a new neutron to proton ratio of about 1:7. This ratio determined the relative amounts of hydrogen and helium produced in the early universe. Approximately 75% of the bionic mass was hydrogen, with about 25% helium by mass, and trace amounts of other light elements. These proportions are observed in the oldest stars and galaxies, confirming the predictions of Big Bang nucleosynthesis. The formation of protons and neutrons also set the stage for the creation of more complex elements. In stars, stars act as cosmic furnaces, fusing hydrogen and helium into heavier elements through nuclear fusion. This stellar nucleosynthesis process builds on the foundation laid by the Big Bang. The stability of protons and neutrons is fundamental to the existence of matter. Protons, being positively charged, would naturally repel each other without the strong force to bind them within nuclei. Neutrons, while neutral, contribute to the stability and binding energy of atomic nuclei. Protons and neutrons are collectively known as nucleons. Their interactions and arrangements within atomic nuclei define the chemical properties of elements. Understanding these particles helps scientists predict the behavior and stability of different isotopes. The study of protons and neutrons extends beyond their role In atomic nuclei high energy physics experiments, such as those conducted in particle accelerators probe, with the internal structure and interactions of these nucleons. This research provides deep insights into the strong nuclear force, the interactions between protons and neutrons also play a role in the forces that govern larger structures in neutron stars. For example, the behavior of neutrons under extreme pressure and density can lead to the formation of exotic states of matter. The properties of protons and neutrons, including their masses and charges, are fundamental constants of nature. These properties influence the behavior of matter and the dynamics of the universe on both small and large scales. Overall, the formation of protons and neutrons was a critical event in the early universe. These particles are the foundation of atomic nuclei and the building blocks of matter. Understanding their formation and interactions is key to understanding the universe's structure and evolution. Nucleosynthesis in the first few minutes of the universe was a critical phase in the formation of elements. This period, known as Big Bang nucleosynthesis, began just seconds after the Big Bang. During this time, temperatures were extremely high, allowing nuclear reactions to occur rapidly as the universe expanded. And cooled protons and neutrons began to combine to form the nuclei of the lightest elements. The first step in this process was the formation of helium, a heavy isotope of hydrogen nuclei, then fused to create helium-3 and helium-4. Helium-4 was the most stable and abundant product of these nuclear reactions. About 25% of the universe's mass was converted into helium-4, while most of the remaining mass remained as hydrogen. This hydrogen-helium ratio is a key piece of evidence for the Big Bang theory. In addition to helium, trace amounts of other light elements were also produced. These included lithium and beryllium. However, the conditions were not suitable for the formation of heavier elements, which would require more complex nuclear reactions. The nucleosynthesis process was very sensitive to the conditions of the early universe. The exact ratios of the light elements depend on the density of baryons and the rate of expansion. Observations of these elemental abundances match the predictions of the Big Bang model. As the universe cooled, further nuclear reactions slowed down and eventually stopped. The universe had expanded too much for nuclei to collide and fuse this freeze out, left a stable mix of hydrogen, helium, and trace amounts of lithium and barium. The light elements formed during Big Bang nucleosynthesis provide a snapshot of the early universe. Their relative abundances have been measured in old stars and interstellar gas clouds, offering a window into conditions just minutes after the Big Bang nucleosynthesis set the stage for the formation of more complex elements in stars formed from the primordial gas of hydrogen and helium, initiating nuclear fusion in their cause. This stellar nucleosynthesis built upon the foundation of light elements created in the Big Bang. The process of Big Bang nuclear synthesis was governed by the fundamental forces of nature. The strong nuclear force bound protons and neutrons together in nuclei, while the weak nuclear force facilitated the conversion of neutrons to protons. These interactions were crucial for the synthesis of light elements. Observations of the cosmic microwave background radiation also support the Big Bang nucleosynthesis model. This radiation provides a snapshot of the universe when it was just 380,000 years old, showing the distribution of matter and energy that resulted from the nucleosynthesis process. Big Bang nucleosynthesis is one of the key pillars of modern cosmology. It provides a direct link between the conditions of the early universe and the observable universe today. The success of this model is a major triumph for the Big Bang theory. Understanding nucleosynthesis helps scientists probe the conditions of the early universe. It reveals how the first elements formed and set the stage for the chemical complexity of the universe. This knowledge is essential for understanding the evolution of matter over cosmic time. Research into Big Bang nuclear synthesis continues to refine our understanding of the early universe. Advances in observational techniques and theoretical models helps scientists test the predictions of the Big Bang model with greater precision. This ongoing work deepens knowledge of the cosmos. The formation of light elements during the first few minutes of the universe was a transformative event. It created the building blocks for all matter and set the chemical composition of the universe. The legacy of Big Bang nucleosynthesis is evident in the stars and galaxies that populate the cosmos. Overall, Big Bang nuclear synthesis was a brief but pivotal period in the history of the universe. It forged the first elements from the primordial soup of particles, laying the groundwork for the complexity and diversity of matter we see today. Understanding this process is key to understanding our origins, the emergence of hydrogen and helium in the early universe was a direct result of Big Bang nucleosynthesis. As the universe cooled, protons and neutrons combined to form these light elements, hydrogen. The simplest element became the most abundant. Hydrogen consists of a single proton and one electron. It formed when protons captured 3 electrons. As the universe cooled, this process created vast amounts of hydrogen gas, which later became the fuel for star formation. Helium, the second most abundant element, form through the fusion of protons and neutrons. Most helium nuclei consist of 2 protons and 2 neutrons, known as helium. 4th element was synthesized in significant quantities during the first few minutes after the Big Bang. Approximately 25% of the universe's bionic mass was converted into helium. For this high abundance of helium is a key piece of evidence supporting the Big Bang theory. It also set the stage for the formation of heavier elements. In stars, the abundance of hydrogen and helium reflects the conditions of the early universe. The rapid expansion and cooling allowed these elements to form before nuclear reactions ceased. Their proportions remain largely unchanged in the universe. Today, hydrogen and helium are the building blocks of stars and galaxies. Stars form from clouds of these elements, initiating nuclear fusion in their cause. This fusion process converts hydrogen into helium, releasing energy that powers the stars. The emergence of hydrogen and helium also influence the universe's large-scale structure. These elements provided the raw material for the first stars and galaxies. Their distribution shaped the formation of cosmic structures over billions of years. The formation of hydrogen and helium was a critical step in the universe's chemical evolution. These elements are essential for the synthesis of more complex atoms in stars. The process of stellar nucleosynthesis builds on the foundation of hydrogen and helium. The study of hydrogen and helium abundances in ancient stars and gas clouds helps scientists understand the early universe. These observations provide a window into the conditions just minutes after the Big Bang, confirming theoretical predictions. Hydrogen and helium play a crucial role in the interstellar medium. They dominate the composition of gas clouds in galaxies, influencing star formation and the dynamics of galactic structures. Their presence shapes the life cycle of stars. The evolution of galaxies. The properties of hydrogen and helium also affect the behavior of the universe on large scales. Hydrogen, being the most abundant element, plays a key role in cooling gas clouds and enabling the collapse of matter to form stars. Helium contributes to the overall mass and dynamics of galaxies. The emergence of these elements is fundamental to our understanding of the cosmos. They are the simplest and most abundant elements, providing the foundation for all matter. Their formation marked a pivotal moment in the universe's history. Hydrogen and helium continue to be central to modern astrophysics. Their spectral lines allow astronomers to study distant galaxies and stars. These elements serve as traces for understanding the composition and evolution of the universe. The legacy of hydrogen and helium formation is evident throughout the cosmos, from the smallest stars to the largest galaxies. These elements are everywhere. They are the building blocks of the universe, influencing its structure and evolution at every scale. Overall, the emergence of hydrogen and helium set the stage for the universe's chemical and structural evolution. These elements are the fundamental ingredients of stars and galaxies, shaping the cosmos as we see it today. Understanding their formation helps us comprehend the universe's origins and development. Matter-antimatter asymmetry is one of the great mysteries of the universe. In theory, the Big Bang should have produced equal amounts of matter and antimatter. However, we observe a universe dominated by matter, with very little antimatter. Antimatter particles are the counterparts of matter particles with opposite charges. When matter and antimatter meet, they annihilate each other, producing pure energy. This process suggests that any initial matter and antimatter should have destroyed each other, that the fact that that matter dominates the universe indicates an asymmetry in the laws of physics. This asymmetry must have favored matter over antimatter in the early universe. Understanding this imbalance is crucial for explaining the existence of the matter we see today. One potential explanation for this asymmetry is the concept of CP violation. CP violation refers to a difference in the behavior of particles and their antiparticles violating charge parity symmetry. This phenomenon has been observed in certain subatomic particles like chons, A and D B muons. The standard model of particle physics includes mechanisms for CP violation, but they are not sufficient to explain the observed matter-antimatter imbalance. This suggests that additional sources of CP violation may exist, possibly involving new physics beyond the standard model. The early universe provided conditions that could amplify CP violation effects during the first moments after the Big Bang. High temperatures and densities could have influenced particle interactions, leading to a slight excess of matter over antimatter. As the universe cooled, this slight excess of matter would have survived, while the remaining matter and antimatter annihilated each other. The result was a universe with a small but significant amount of matter, forming the basis for all cosmic structures. Experiments at particle accelerators aim to study CP violation in greater detail by observing the behavior of particles and antiparticles under controlled conditions. Scientists hope to uncover new sources of asymmetry. These experiments could provide insights into the early universe's conditions. In addition to laboratory experiments, astrophysical observations contribute to our understanding of matter-antimatter asymmetry. Studying cosmic rays and the distribution of antimatter in the universe helps researchers test theoretical models and refine their predictions. The matter-antimatter asymmetry also has implications for the overall balance of the universe. The observed dominance of matter influences the formation and evolution of galaxies, stars, and planets. Without this imbalance, the universe would be vastly different. The question of why the universe is made of matter rather than antimatter touches on fundamental aspects of cosmology and particle physics. It connects the smallest scales of particle interactions with the largest scales of cosmic structures. Theoretical models addressing matter-antimatter asymmetry often involve extensions to the Standard Model. These models propose new particles or interactions that could generate the required CP violation testing. These models is a major focus of current research. The interplay between matter-antimatter and the forces governing their interactions continues to be a rich field of study. Discoveries in this area have the potential to reshape our understanding of the universe's origins and fundamental laws. Understanding matter-antimatter asymmetry is key to answering profound questions about the nature of existence. It challenges our comprehension of why the universe is the way it is, and opens pathways to new physics. The journey to uncover the reasons behind matter-antimatter asymmetry is ongoing. Each new experiment and observation brings us closer to solving this cosmic puzzle. The quest to understand this imbalance is central to our broader quest to understand the universe itself. The recombination era was a pivotal phase in the early universe, occurring around 380 years after the Big Bang. It marked the time when the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This process had profound implications for the evolution of the cosmos. Before recombination, the universe was a hot, dense plasma of free electrons and protons. Light could not travel far without scattering off these free electrons, making the universe opaque. As the universe expanded and cooled, conditions allowed electrons to bind with protons, creating neutral atoms. The formation of neutral hydrogen atoms allowed photons to travel freely. For the first time, this decoupling of matter and radiation resulted in the universe becoming transparent. The light from this era is what we now observe as the cosmic microwave background radiation. The cosmic microwave background provides a snapshot of the universe at the moment of recombination. It shows tiny fluctuations in temperature, reflecting the initial density variations that would later grow into galaxies and large-scale structures. This radiation offers critical insights into the early universe. The temperature of the universe during recombination dropped to about 3,000 Kelvin. At this temperature, the binding energy of hydrogen was sufficient to keep electrons and proto-NS together. The transition from a plasma to a neutral gas significantly altered the universe's properties. Recombination did not happen instantaneously, but occurred over a period of time as the universe continued to expand. More electrons combined with protons, gradually increasing transparency. This era marks a significant change in the interaction between light and matter. The era of recombination also influenced the formation of the first structures in the universe. The decoupling of matter and radiation allowed gravitational collapse to proceed more efficiently, leading to the growth of the RST stars and galaxies. These structures began to form from the initial density fluctuations. The cosmic microwave background radiation, or CMB, is a crucial piece of evidence for the Big Bang theory. It is remarkably uniform, with tiny temperature variations that correspond to the seeds of future structures. Studying the CMB has helped cosmologists refine models of the early universe observations of the CMB by satellites such as COBE-WMAP and Planck have provided detailed map of these temperature fluctuations. These maps help scientists understand the conditions of the early universe and the process that led to the formation of galaxies and clusters. Recombination also had an impact on the chemical evolution of the universe. The creation of neutral hydrogen and helium atoms set the stage for the formation of molecular clouds. These clouds eventually collapsed under gravity to form the first stars, initiating the process of stellar nucleosynthesis. The free electrons remaining after recombination played a role in the ionization of the universe. As the first stars in galaxies formed, their radiation rise the neutral hydrogen, making the universe transparent to ultraviolet light. This risation epoch followed the era of recombination. The study of recombination helps cosmologists understand the transition from the hot, dense, early universe to the cooler, structured universe we see today. It bridges the gap between the initial conditions set by the Big Bang and the later formation of complex structures. Detailed measurements of the CMB provide a wealth of information about the universe's composition, age, and rate of expansion. These observations have confirmed key predictions of the Big Bang model and helped refine our understanding of cosmological parameters. The recombination era marks the beginning of the universe's ability to form stars and galaxies. It set the initial conditions for the growth of structure, influencing the distribution of matter and the large-scale architecture of the cosmos. Understanding the recombination era is essential for constructing accurate models of cosmic evolution. It connects the physics of the early universe with the formation and development of the structures that populate the universe today. This era is a cornerstone of modern cosmology. The formation of neutral atoms was a significant milestone in the universe's history. As the universe cooled, protons and electrons combined to form hydrogen atoms. This process occurred around 380 years after the Big Bang. Before this period, the universe was filled with a hot, dense plasma of charged particles. Photons were constantly scattered by free electrons, making the universe opaque. As the temperature dropped, electrons began to bind with protons. This recombination of protons and electrons marked the transition from a plasma to a gas of neutral atoms. Hydrogen atoms formed first, followed by helium. The creation of neutral atoms allowed photons to travel freely. For the first time, the universe became transparent, and the light from this era is observed today as the cosmic microwave background radiation. This radiation provides a snapshot of the universe at the moment neutral atoms formed. It carries information about the early universe's conditions. The formation of neutral atoms was a gradual process, not an instantaneous event. As the universe expanded and cooled, more electrons combined with protons over time. This period of recombination resulted in a significant change in the universe's properties. The creation of neutral atoms had profound implications for the future development of the universe. It allowed the first light to travel unimpeded, setting the stage for the formation of stars and galaxies. The universe transitioned from an opaque plasma to a transparent gas. This transition also influenced the universe's large-scale structure. The density fluctuations present at recombination grew under the influence of gravity. These fluctuations eventually led to the formation of the first stars in galaxies. The study of the cosmic microwave background radiation provides insights into this era. the tiny variations in temperature observed in the CMB reflect the initial density fluctuations. These fluctuations are the seeds of all future cosmic structures. As neutral atoms formed, the universe's overall temperature continued to drop. The formation of hydrogen and helium atoms significantly reduced the number of free electrons. This reduction in scattering allowed the universe to become more transparent. The formation of neutral atoms also had an impact on the chemical evolution of the universe. These atoms served as the building blocks for more complex molecules over time. These molecules contributed to the cooling and collapse of gas clouds, leading to star formation. Neutral hydrogen atoms played a crucial role in the early universe's cooling process. They allowed the universe to cool more efficiently, facilitating the formation of molecular hydrogen. Molecular hydrogen was essential for the formation of the first stars. The first stars formed from these cooled gas clouds initiated the process of reionization. The radiation from these stars reionized the neutral hydrogen, making the universe transparent to ultraviolet light. This radiation epoch followed the era of recombination. The formation of neutral atom set the stage for the universe's subsequent evolution. It allowed for the development of complex structures from stars and galaxies to clusters and superclusters. This era was a turning point in the universe's history. Understanding the formation of neutral atoms helps cosmologists piece together the timeline of cosmic events. It provides a link between the hot, dead, early universe and the structured, cooler universe we observe today. This knowledge is essential for understanding the universe's evolution. The era of recombination and the formation of neutral atoms are central to our understanding of cosmology. They mark the beginning of the universe's ability to form stars, galaxies, and all subsequent structures. This period is a crucial chapter in the story of the cosmos. The cosmic microwave background radiation, or CMB, is relic from the early universe. It was emitted approximately 380,000 years after the Big Bang, during the era of recombination. This radiation provides a snapshot of the universe at that time. The CMB is the oldest light we can observe. It fills the entire universe and is almost perfectly uniform. tiny fluctuations in its temperature reveal the seeds of future cosmic structures. These temperature fluctuations in the CMB are incredibly small, just ni part in 100,000. They correspond to slight differences in density in the early universe. These differences eventually led to the formation of galaxies and clusters. The CMB was first detected in 1965 by Arup Penzias and Robert Wilson. They discovered it as a faint background noise in their radio antenna. This discovery provided strong evidence for the Big Bang theory. The study of the CMB has become a cornerstone of cosmology. Detailed measurements have been made by satellites such as Cobb WMAP and Planck. These observations have provided a wealth of information about the universe's early conditions. The CMB has a characteristic black body spectrum, indicating it was once in thermal equilibrium. Its peak temperature is about 2,725 Kelvin, just above absolute zero. This uniform temperature supports the idea of a hot, dense, early universe. The tiny variations in the CNB's temperature are imprints of the initial density fluctuations. These fluctuations were amplified by gravity, leading to the large-scale structure of the universe. The pattern of these fluctuations matches predictions from the Big Bang model. The polarization of the CMB also carries important information. Polarization arises from the SC uttering of light by free electrons in the early universe. This data helps scientists understand the physics of the early universe and the effects of inflation. The CMB also provides insights into the universe's composition and geometry. Measurements of the CNB's anisotropies help determine the densities of dark matter, dark energy, and normal matter. This information is crucial for understanding the universe's evolution. The study of the CMB has confirmed the existence of dark matter and dark energy. These components influence the CNB's temperature fluctuations and polarization. Understanding their effects help scientists refine models of the universe. The CM's uniformity and slight entropies are key pieces of evidence for the Big Bang theory. They support the idea that the universe began as a hot, dense state and has been expanding ever since. This discovery has revolutionized our understanding of the cosmos. The CMB also helps scientists test theories of cosmic inflation, predicts a specific pattern of fluctuations in the CMB observations, have so far been consistent with these predictions, providing strong support for the inflationary model. In addition to its scientific significance, the CMBB is a fascinating subject of study. It represents a direct link to the universe's infancy. Studying it helps us understand our cosmic origins and the processes that shape the universe. The ongoing study of the CMB continues to reveal new insights. Each new observation helps refine our understanding of the early universe and the fundamental laws of physics. The CMBB remains a vital tool for cosmologists. Overall, the cosmic microwave background radiation is a cornerstone of modern cosmology. It provides a window into the early universe and supports the Big Bang theory. Understanding the CMB helps us unravel the mysteries of the cosmos. The universe becomes transparent during the era of recombination. This critical phase occurred around 380 years after the Big Bang. As the universe cooled, protons and electrons combined to form neutral hydrogen atoms before recombination. The universe was a hot, dense plasma. Photons were constantly scattered by free electrons, making the universe opaque. Once neutral atoms formed, photons could travel freely, leading to transparency. This transition allowed light to decouple from matter. The photons released during this time form the cosmic microwave background ND radiation. This radiation provides a snapshot of the universe. At the moment, it became transparent. The transparency of the universe marked a significant change. It set the stage for the formation of the first stars and galaxies. With light traveling freely, the universe entered a new phase of evolution. As the universe expanded and cooled, it transitioned from an opaque plasma to a transparent gas. This change allowed the initial density fluctuations to grow under gravity. These fluctuations eventually led to the large-scale structures we observe today. The cosmic microwave background radiation is a direct result of this transparency. It carries information about the conditions of the early universe. The tiny fluctuations in the CMB reveal the seeds of future cosmic structures. The transition to transparency also influenced the chemical evolution of the universe. The formation of neutral hydrogen and helium atoms allowed for the cooling and collapse of gas clouds. These clouds later form the first stars. This period of transparency is crucial for understanding the universe's history. It connects the early hot, dense phase with the later cooler, structured phase, pH. Studying this transition helped us scientists piece together the timeline of cosmic events. The transparency of the universe allowed for the development of complex structures. Without this transition, the universe would remain a hot, dense plasma, preventing the formation of stars and galaxies. This period set the initial conditions for cosmic evolution. The transition to transparency was not instantaneous, but occurred over a period of time as the universe continued to expand and cool. More electrons combined with protons. This gradual process led to increasing transparency. The study of the microwave background radiation provides insights into this transition. The CM's uniformity and tiny anisotropies reflect the conditions at the time of recombination. This data is essential for understanding the early universe. The transparency of the universe allowed light to travel unimpeded for the first time. This light, now observed as the CMB, provides a wealth of information about the early universe. It helps scientists refine models of cosmic evolution. The transition to a transparent universe also had implications for the reionization epoch. The first stars and galaxies formed after recombination, emitting radiation that re-en the neutral hydrogen. This process made the universe transparent to ultraviolet light. Understanding the transition to transparency is essential for constructing accurate cosmological models. It provides a link between the Big Bang and the later formation of stars and galaxies. This period is a crucial chapter in the universe's history. Overall, the universe becoming transparent was a pivotal event. It marked the end of the hot, dense plasma phase and the beginning of the universe as we know it. Studying this transition helps us understand the origins and evolution of the cosmos. Dark matter plays a crucial role in the structure and evolution of the universe. Although it does not emit or absorb light, its presence is inferred from its gravitational effects on visible matter. It makes up about 27% of the universe's total mass energy content. The existence of dark matter was first proposed to explain the rotation curves of galaxies. Observations showed that the outer regions of galaxies rotate faster than can be accounted for by visible matter alone. This discrepancy suggests the presence of unseen mass dark matter acts as a cosmic scaffold, influencing the formation and growth of galaxies. It clumps together under the force of gravity, creating potential wells where visible matter can accumulate. These regions of high dark matter density are the birthplaces of galaxies. In the early universe, dark matter played a key role in the formation of large-scale structures. It began to clump together long before ordinary matter could cool and form structures. These dark matter clumps provided the gravitational pull needed for gas to collapse and form the first stars and galaxies. The cosmic microwave background radiation provides indirect evidence for dark matter. The patterns of temperature fluctuations in the CMB are influenced by the presence of dark matter. These patterns help cosmologists determine the amount and distribution of dark matter in the early universe. Dark matter also affects the motion of galaxies within galaxy clusters. Observations of galaxy clusters reveal that there is much more mass present than can be accounted for by visible matter alone. This additional mass is attributed to dark matter. Gravitational lensing is another phenomenon that provides evidence for dark matter. Light from distant objects is bent by the gravitational field of massive objects, including dark matter. The study of these lensing effects helps map the distribution of dark matter in the universe. Despite its significant effects on cosmic structures, dark matter remains elusive. It interacts with ordinary matter primarily through gravity, making it difficult to detect directly. Various experiments are underway to try to identify dark matter particles. Understanding dark matter is essential for a complete picture of cosmic evolution. It influences the formation of galaxies, the dynamics of galaxy clusters, and the overall structure of the universe. Without dark matter, the universe would look very different. The nature of dark matter is one of the biggest mysteries in modern physics. Several candidates have been proposed, including weakly interacting massive particles, or WIMPs, and a determining which, if any, of these particles constitute dark matter is a major focus of current research. Dark matter's gravitational influence extends over large cosmic scales. It helps to bind galaxies together, preventing them from flying apart due to their rotational speeds. This binding effect is crucial for the stability of galaxies. The search for dark matter includes both direct detection experiments and indirect methods. Direct detection involves attempting to absorb OBV dark matter particles interacting with ordinary matter in highly sensitive detectors. Indirect methods include observing the effects of dark matter on cosmic structures. The role of dark matter in galaxy formation is particularly significant. Without it, the gravitational pull would be insufficient to form galaxies as quickly as they did. Dark matter's presence accelerates the process of galaxy formation, leading to the rich structure we observe in the universe today. Research into dark matter continues to advance our understanding of the universe. Each discovery brings us closer to uncovering the true nature of this mysterious substance. It remains a fundamental component of cosmological models and theories. Overall, dark matter is a vital, though invisible, player in the cosmic story. Its influence shapes the universe on every scale, from the smallest galaxies to the largest superclusters. Understanding dark matter is key to unlocking the secrets of the cosmos. The gravitational collapse of gas clouds is a fundamental process in star formation. When a region within a gas cloud reaches a critical density, gravity overcomes internal pressure, causing the cloud to collapse. This leads to the birth of new stars. As the gas cloud collapses, it fragments into smaller clumps. Each clump can form one or more stars, depending on its mass. The collapse process increases the temperature and pressure within the clumps. In the center of each collapsing clump, a protostar forms. The material continues to fall inward, increasing the protostar's mass and temperature. Eventually, the core temperature becomes high enough for nuclear fusion to begin. During the collapse, conservation of angular momentum causes the gas to spin faster. This can lead to the formation of a rotating disk around the protostar. These disks are the birthplaces of planets and other stellar objects. Magnetic fields and turbulence within the gas cloud can influence the collapse process. They can cause the cloud to fragment differently, affecting the number and types of stars formed. Magnetic fields can also drive powerful jets of material away from the protostar. The collapse of gas clouds also leads to the formation of star clusters. Stars often form in groups as the collapse of a single large gas cloud can produce many stars. These clusters can remain bound by gravity or disperse over time. Gravitational collapse can trigger further star formation in nearby regions. The energy released by newly formed stars can compress adjacent gas clouds, initiating collapse in those regions. This process is known as triggered star formation. The initial mass of the collapsing gas cloud determines the type of star that forms. More massive clouds produce hotter, more massive stars, while smaller clouds form cooler, less massive stars. This range of types contributes to the diversity of the cosmos. Observations of star-forming regions, such as the Orion Nebula, provide insights into the collapse process. Telescopes can detect the infrared and radio emissions from protostars and their surrounding disks. These observations help scientists understand the details of star form. The collapse of gas clouds is influenced by the presence of dark matter. Dark matter's gravitational pull can enhance the collapse process, leading to more efficient star formation. This interaction between dark matter and gas clouds shapes the structure of galaxies. Gravitational collapse is also a key factor in the formation of giant molecular clouds. These massive clouds are the SES of intense star formation active. They contain vast amounts of gas and dust, providing the raw material for new stars. The process of gravitational collapse continues to play a vital role in the evolution of galaxies. It drives the cycle of star formation and death, enriching the interstellar medium with heavy elements. These elements are then incorporated into new generations of stars and planets. Understanding gravitational collapse helps scientists predict the future evolution of galaxies. It reveals the conditions necessary for star formation and the factors that influence it. This knowledge is crucial for constructing accurate models of galaxy evolution. Overall, the gravitational collapse of gas clouds is a fundamental process in the universe. It leads to the formation of stars and planetary systems, shaping the structure and evolution of galaxies. Studying this process provides essential insights into the dynamics of the cosmos population. The 3 stars were the first stars to form in the universe. They emerge from the primordial gas clouds, composed mostly of hydrogen and helium. These stars played a crucial role in shaping the early universe. Unlike later generations of stars' population, 3 stars contained almost no heavier elements. This lack of metals is due to their formation from primordial gas, which had not yet been enriched by previous generations of stars. Their formation marked the end of the cosmic dark ages population. The 3 stars were likely very massive, some reaching up to hundreds of times the mass of the Sun. Their high mass led to short lifespans and extremely hot, bright emissions. These stars significantly influence their surroundings through intense radiation. The radiation from population. 3 stars ionized the surrounding hydrogen gas, contributing to the risation of the universe. This process made the universe transparent to ultraviolet light, allowing light from these stars to travel freely. Risation was a key event in cosmic history. Due to their massive size population, the 3 stars quickly exhausted their nuclear fuel. Their short lifespans, often just a few million years, ended in violent supernova explosions. These explosions seeded the universe with the first heavy elements, the supernovae of population. 3 stars enriched the interstellar medium with elements like carbon, oxygen, and iron. These elements became the building blocks for later generations of stars and planets. This process of enrichment is known as chemical evolution. Observing population 3 stars directly is challenging because they existed so long ago. However, their influence can be inferred from the chemical composition of ancient stars and galaxies. These observations help scientists understand the conditions of the early universe. Simulations of the early universe provide insights into the formation of population. 3 stars. These models suggest that they formed in small, dense regions within primordial gas clouds. The gravitational collapse of these regions led to the birth of the first stars. The formation of population 3 stars also trigger the formation of subsequent generations of stars. the heavy elements produced in their supernova acted as catalysts for star formation in later gas clouds. This process set the stage for the development of complex cosmic structures, population. The Thur stars are thought to have been responsible for the first black holes. When these massive stars ended their lives, they collapsed into black holes. These early black holes may have merged and grown, contributing to the formation of supermassive black holes. In galaxies, the study of population, THRE stars, helped scientists understand the early stages of galaxy formation. These stars provided the initial bursts of light and energy that transformed the universe. Their existence marked the transition from a dark, featureless cosmos to a complex, structured one. Research into population, Three stars, continues to be an active field in astronomy. Advances in telescopes and simulations are bringing us closer to observing the remnants and influences of these ancient stars. Each discovery adds to our understanding of the universe's formative years. The legacy of population, three stars, is evident in the cosmic structures we see today. Their role in radiation, chemical enrichment, and black hole formation shape the evolutionary path of the universe. Understanding these stars is key to unraveling the history of the cosmos. Population, the three stars also provide a benchmark for testing models of star formation and cosmic evolution. Their unique characteristics offer insights into the fundamental processes that govern the universe. Studying these stars helps refine our theoretical frameworks. Overall, the formation of population, three stars, was a pivotal event in the history of the universe. These first stars illuminated the cosmos, initiated ranas, and enriched the interstellar medium. Their impact set the stage for all subsequent cosmic evolution. The first galaxies formed from the gravitation, collapse of gas, and dark matter. These early galaxies were small and irregular in shape, composed mostly of hydrogen and helium gas. They marked the beginning of large-scale structure formation in the universe. As gas clouds within these proto-galaxies cooled, they fragmented into clumps, leading to the formation of stars. The first stars, known as population three stars, were massive and short-lived. Their supernova enriched the surrounding gas with heavier elements. These early galaxies were sites of intense star. For formation, the energy released by new stars and supernovae helped shape the galaxies, driving the evolution of their structure. The feedback from star formation played a crucial role in regulating the growth of galaxies. The first galaxies were influenced by dark matter, which provided the gravitational scaffolding needed for their formation. Dark matter halos formed around the galaxies, enhancing their gravitational pull and helping them attract more gas and matter. The process of galaxy formation involved mergers and interactions. Small proto-galaxies collided and merged to form larger galaxies. These interactions contributed to the diversity of galaxy shapes and sizes observed in the universe. Today, observations of distant galaxies provide a glimpse into the early universe. Telescopes like Hubble and James Webb are capable of observing galaxies that form less than 1 billion years after the Big Bang. These observations help us understand the properties of the first galaxies. The first galaxies played a key role in the risation of the universe. The intense ultraviolet radiation from young stars ionized the surrounding hydrogen gas. This risation made the universe transparent to ultraviolet light and allowed light from distant galaxies to reach us. Galaxy formation continued over billions of years, leading to the rich variety of galaxies we see today. Spiral, elliptical, and irregular galaxies evolved from the interactions and merges of earlier generations of galaxies. Each type has distinct properties and histories. The first galaxies were relatively small compared to the massive galaxies we see today. However, they laid the foundation for the growth of larger galaxies over time. These early structures merged and accumulated more mass, evolving into the galaxies we observe in the present universe. Supermassive black holes likely formed in the centers of some of the first galaxies. These black holes grew by accreting gas and merging with other black holes. They played a significant role in the evolution of their host galaxies, affecting star formation and galactic dynamics. The study of the first galaxies helps astronomers understand the initial conditions of the universe. By analyzing the light from these distant objects, scientists can infer the processes that drove galaxy formation. and de-evolution. This research provides a window into the universe's infancy. Computer simulations of galaxy form offer valuable insights into the behavior of the early universe. These simulations model the gravitational interactions between dark matter and gas, reproducing the formation and evolution of galaxies. They help validate theories of cosmic structure formation. The first galaxies were rich in gas, providing the material needed for star formation. As stars formed and died, they enriched the gas with heavier elements, creating the conditions for the formation of planets and complex chemistry. This process set the stage for the development of life. The evolution of galaxies is influenced by their environments. Galaxies in dense regions, such as galaxy clusters, experience more frequent interactions and mergers. These environments can accelerate the growth and evolution of galaxies, leading to a wide range of galactic properties. Understanding the formation of the first galaxies is crucial for a comprehensive view of cosmic history. These early structures laid the groundwork for the complex universe we see today. Studying them helps us piece together the story of the cosmos, from its earliest moments to the present. Supermassive black holes are found at the centers of most galaxies. Their masses range from millions to billions of times that of the Sun. These black holes play a significant role in the formation and evolution of galaxies. The origin of supermassive black holes is still a topic of research. They may have formed from the collapse of massive gas clouds in the early universe, or from the merges of smaller black holes. Their growth is influenced by the accretion of gas and the merging of other black holes. Supermassive black holes influence their host galaxies through their immense gravitational pull. They can affect the orbits of stars and gas in the galaxy's core. This gravitational influence helps shape the central regions of galaxies. The accretion of matter onto supermassive black holes releases enormous amounts of energy. This process powers cores, which are among the brightest objects in the universe. Cores can outshine their entire host galaxies. The energy emitted by supermassive black holes can drive powerful jets of particles. These jets can extend far beyond the host galaxy, impacting the intergalactic medium. They can heat the surrounding gas, inhibiting further star formation supermassive black holes regulate the growth of galaxies through feedback mechanisms. The energy and jets they produce can expel gas from the galaxy, limiting the amount of material available for stars' formation. This feedback helps prevent galaxies from becoming too massive too quickly. The relationship between a galaxy and its central supermassive black hole is evident in the tight correlation between the mass of the black hole and the mass of the galaxy's bulge. This correlation suggests a coevolution where the growth of the black hole and the galaxy are interconnected. Observe at ions of active galactic nuclei, or AGN, provide insights into the behavior of supermassive black holes. AG are powered by accreting supermassive black holes and can vary in brightness over time. Studying AGN helps us understand the accretion processes in the environments of these black holes. Supermassive black holes also play a role in galaxy mergers. When galaxies merge, their central black holes can eventually coalesce, forming an even more massive black hole. The merging process can generate gravitational waves, ripples in space-time, that we can detect the presence of supermassive black holes. Can I influence the distribution of stars in a G galaxy? They can create regions of high stellar density in the galaxy's core. These dense regions, called stellar bulges, are common in many galaxies. Understanding the formation and growth of supermassive black holes is crucial for a complete picture of galaxy evolution. Their influence extends far beyond their immediate surroundings, affecting the entire galaxy and even the intergalactic medium. Future observations with advanced telescopes, such as the James Webb Space Telescope, will provide more detailed views of supermassive black holes and their host galaxies. These observations will help unravel the mysteries of how these massive objects form and grow. The study of gravitational waves from merging black holes offers a new way to explore the universe. These waves carry information about the black holes, masses, and spins, providing insights into their formation and evolution. Supermassive black holes are essential for understanding the dynamics of galaxies, their interactions with stars, gas, and other black holes reveal the complex processes that shape galaxies over cosmic time. They are key players in the story of cosmic evolution, overall supermass. Black holes are fundamental components of galaxies. Their impact on star formation, galaxy growth, and the intergalactic medium highlights their importance in the universe. Understanding them is crucial for unraveling the full story of galaxies and their evolution. The evolution of galaxies over time is a dynamic and complex process. Galaxies form from initial gas clouds, which collapse under gravity to create stars and structures. These early galaxies are small and irregular in shape. As galaxies grow, they interact and merge with one another. These merges are fundamental in shaping the structure of galaxies. Collisions can trigger intense bursts of star formation and lead to the formation of larger, more massive galaxies. Galaxy evolution is influenced by the environment. Galaxy in dense clusters interact more frequently than those in isolated regions. These interactions can strip galaxies of their gas, alter their shapes, and even result in galaxy cannibalism. Spiral galaxies, like our Milky Way, are characterized by their rotating disk structure. Over time, the formation of spiral arms is influenced by the galaxy's rotation and gravitational interactions. These galaxies often have ongoing star formation in their disks. Elliptical galaxies are typically older and have less active star formation. They formed from the merges of smaller galaxies, resulting in a more uniform ellipsoidal shape. These galaxies contain older, redder stars and less interstellar gas and dust. Irregular galaxies lack a defined shape. They are often the result of gravitational interactions and merges. These galaxies can be rich in gas and dust, leading to new star formation. Despite their chaotic appearance, the star formation rate in galaxies changes over time. Early in the universe, star formation was much more intense. As galaxies evolve, the available gas is consumed, and star formation slows down. Galactic feedback processes play a crucial role in evolution. Supernova, stellar winds, and black hole activity can expel gas from galaxies. This feedback regulates star formation and prevents galaxies from becoming too massive too quickly. Dark matter halos are essential in the evolution of galaxies. They provide the gravitational framework that helps galaxies form and grow. The interaction between dark matter and bionic matter influences the distribution of stars, and gas, the morphology-density relation, describes how galaxy type E's vary with environment-dense regions, like galaxy clusters, have more elliptical and lenticular galaxies. This relation highlights the impact of the local environment on galaxy evolution. Galaxies evolve through different phases, active phases with high star formation rate, and quasar activity transition into more quiescent phases. These changes are driven by internal processes and external interactions. Galaxy clusters evolve over time. As well, they grow by accreting smaller groups and individual galaxies. The interactions within clusters can strip galaxies of gas quench star formation and alter IR shapes. Observations of distant galaxies provide snapshots of different stages of evolution. Telescopes like Hubble and James Webb can see galaxies at various stages, helping us understand the timeline of galactic development. Computer simulations of galaxy evolution offer detailed insights. These models incorporate physics from dark matter interactions to star formation and feedback simulations, help predict how galaxies evolve under different conditions. The study of galaxy evolution is crucial for understanding the universe's history. It connects the formation of the first galaxies to the rich diversity we see today. Each galaxy's evolution story contributes to our overall picture of cosmic history. Merging and interaction of galaxies are fundamental processes in their evolution. When galaxies pass close to each other, their mutual gravitational attraction causes them to interact. These interactions can lead to significant structural changes. Galaxy merges can trigger bursts of star formation as gas clouds within the galaxies collide and compress. They can form new stars at an accelerated rate. These star bursts can make merging galaxies some of the brightest objects in the universe. During a merger, galaxies can exchange material and stars. This process can mix the stellar populations of both galaxies, leading to a more homogeneous distribution of stars. The merger can also trigger the formation of new structures, such as tidal talls and bridges. Major mergers involving galaxies of similar size can lead to the formation of elliptical galaxies. The violent interactions during a major merger disrupt the disk structures of the progenitor galaxies. The result is a more rounded, elliptical shape, minor mergers, where a larger galaxy absorbs a smaller one. Are also common. These interactions can add new material to the larger galaxy, including gas dust and stars over time. Minor mergers can significantly increase the mass of a galaxy. Galactic cannibalism is a specific type of interaction where a larger galaxy devours a smaller one. The smaller galaxy is gradually torn apart by tidal forces, and its material is assimilated into the larger galaxy. This process can significantly alter the larger galaxy. Structure interactions can also lead to the formation of galaxy clusters. Groups of galaxies can fall together under their mutual gravitational attraction. Within these clusters, galaxies interact frequently, further influencing their evolution. The dynamics of galaxy interactions are complex. The outcomes depend on factors such as the relative sizes, orientations, and velocities of the galaxies involved. Each interaction is unique, contributing to the diversity of galaxy shapes and sizes observed in the universe. Observations of interacting galaxies provide valuable insights into these processes. Telescopes like Hubble have captured stunning images of galaxies in various stages of interaction and merger. These observations help astronomers understand the mechanics of galactic evolution. The Milky Way itself has experienced numerous merges throughout its history. It is currently absorbing the Sagittarius dwarf galaxy, and it is expected to merge with the Andromeda galaxy in about 5 billion years. These events will reshape our galaxy dramatically. Computer simulations play a crucial role in studying galaxy merges. They allow astronomers to model the complex gravitational interactions and predict the outcomes of different scenarios. These simulations help refine our understanding of how galaxies evolve. Galaxy interactions can also trigger the activity of supermassive black holes as gas is funneled toward the galactic center during a merger. It can fuel the black hole, leading to the formation of active galactic nuclei or quasars. This activity can influence the evolution of the host galaxy. Tidal forces during interactions can strip gas and stars from galaxies, creating long streams of material known as tidal tails. These structures can stretch for hundreds of thousands of light years and are a signature of past interactions. Interactions can also lead to the formation of ring galaxies. If a smaller galaxy passes through the center of a larger disk galaxy, it can create a ripple effect, forming a ring of intense star formation. These rare and beautiful structures are direct evidence of past collisions. Understanding the merging and interaction of galaxies is essential for a comprehensive view of cosmic evolution. These processes drive the growth and transformation of galaxies over billions of years. Each merger and interaction adds to the rich tapestry of the universe's history. The formation of galaxy clusters begins with the gravitational collapse of large regions of dark matter and gas. These clusters are the largest gravitationally bound structures in the universe. Over time, smaller groups of galaxies merge to form these massive clusters. Dark matter plays a crucial role in the formation of galaxy clusters. Its gravitational pull attracts gas and galaxies, creating dense regions where clusters can form. The distribution of dark matter within these clusters influences their overall structure. As galaxies fall into clusters, they interact and merge. These interactions can strip galaxies of their gas, quenching star formation. The hot intercluster medium filled with ionized gas also inhibits the cooling of gas within galaxies. The largest clusters contain thousands of galaxies. These galaxies are often elliptical and have undergone significant merging and interaction. The central galaxy in a cluster known as the brightest cluster galaxy is usually the most massive and can dominate the cluster's core. Galaxy clusters continue to grow by accreting smaller groups and individual galaxies. This hierarchical formation process means that clusters are constantly evolving. Observations of clusters at different stages of development provide insights into their growth. The hot gas in galaxy clusters emits X-rays. Observations with X-ray telescopes reveal the distribution and temperature of this intracluster medium. This hot gas makes up a significant portion of the cluster's total mass. Gravitational lensing is a powerful tool for studying galaxy clusters. The massive gravitational field of a cluster can bend and magnify light from background objects. This effect allows astronomers to map the distribution of dark matter within clusters, the dynamics of galaxy clusters provide information about the universe's expansion. By measuring the velocities of galaxies within clusters, astronomers can infer the cluster's total mass. This data helps refine models of cosmic structure formation. Clusters of galaxies often contain massive galaxy mergers. These mergers can create shock waves in the intercluster medium, heating the gas and affecting the cluster's evolution. These processes can be observed in the X-ray and radio wavelengths. The study of galaxy clusters is crucial for understanding the large-scale structure of the universe. Clusters are nodes in the cosmic web connected by filaments of dark matter and gas. They provide a laboratory for studying the interplay between dark matter, gas, and galaxies. Clusters also serve as important cosmological probes. Their abundance and distribution can be used to test models of dark energy and the overall geometry of the universe. Observing clusters at different red shifts helps track the growth of structure over cosmic time. The interaction of galaxies within clusters leads to a variety of observable phenomena. Ram pressure stripping, where a galaxy's gas is removed by the intercluster medium, can be seen in galaxy talls. These interactions affect the star formation rates and morphologies of cluster galaxies. Galaxy clusters are sites of intense gravitational interactions. The strong gravitational fields can create features such as arcs and rings. Through lensing, these features provide detailed information about the cluster's mass distribution. Understanding the formation and evolution of galaxy clusters helps astronomers piece together the history of the universe. Clusters trace the growth of cosmic structures from the early universe to the present day. They reveal the processes that govern the formation of galaxies and large-scale structures. The study of galaxy clusters continues to evolve with new observations and simulations. Advanced telescopes and instruments are providing deeper insights into these massive structures. As our understanding grows, so too does our knowledge of the universe's evolution. Dark matter is a fundamental component of the universe, influencing the formation and evolution of galaxies and clusters. It interacts with normal matter primarily through gravity, shaping the large-scale structure of the cosmos. Despite its importance, dark matter remains invisible and undetectable by direct observation. The presence of dark matter was first inferred from its gravitational effects. Observations of galaxy rotation curves revealed that visible matter alone could not account for the observed speeds. This discrepancy pointed to the existence of unseen mass, now known as dark matter. Dark matter makes up about 27% of the universe's total mass energy content. It is essential for the formation of galaxies, providing the gravitational pull needed to collapse gas clouds and initiate star formation. Without dark matter, galaxies, as we know them, could not exist in galaxy clusters. Dark matter dominates the total mass. It holds clusters together, preventing them from dispersing. The distribution of dark matter within clusters can be mapped through gravitational lensing, which bends and magnifies the light from background objects. The cosmic web, a vast network of interconnected filaments and voids, is shaped by dark matter. Galaxies and clusters form at the intersections of these filaments, where dark matter density is highest. The cosmic web structure reflects the influence of dark matter on cosmic scales. Dark matter also affects the dynamics of galaxy interactions and mergers. It can influence the orbits of galaxies within clusters and alter their shapes. The presence of dark matter helps stabilize galaxies against tidal forces. During interactions, the nature of dark matter remains one of the biggest mysteries in cosmology. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions. Efforts to detect these particles directly are ongoing using highly sensitive detectors. Indirect evidence for dark matter comes from the cosmic microwave background radiation. The temperature fluctuations in the CMB reveal the distribution of matter in the early universe. These patterns are consistent with the presence of dark matter shaping the universe's evolution. Simulations of cosmic structure formation rely heavily on dark matter. These simulations model how dark matter clumps together to form halos, which then attract gas and form galaxies. Comparing these models to observations helps refine our understanding of dark matter's role. Dark matter's influence extends to the formation of stars and planetary systems in regions of high dark matter density. Gas clouds can collapse more efficiently, leading to increased star formation. Dark matter's gravitational pull helps concentrate the material needed for star formation. The study of dark matter has also led to insights into the behavior of normal matter. Observations of galaxy clusters show that dark matter can separate from normal matter. During collisions, this separation provides clues about the properties and interactions of dark matter. Understanding dark matter is crucial for a complete picture of the universe's history. It affects everything from the smallest scales of star formation to the largest scales of galaxy clusters. Dark matter's gravitation influence is a key driver of cosmic evolution. Future observations and experiments aim to uncover the true nature of dark matter. Advanced telescopes, particle detectors, and simulations will continue to probe its properties. Each discovery brings us close to understanding this elusive and fundamental component of the universe. The influence of dark matter is evident in the distribution and behavior of galaxies and clusters. It provides the gravitational framework that underpins the structure of the universe. Studying dark matter helps us understand the forces that shape the cosmos. Dark matter remains one of the most intriguing and essential aspects of modern cosmology. Its influence permeates the universe, driving the formation and evolution of cosmic structures. Unlocking the secrets of dark matter is key to unraveling the mysteries of the universe. Superclusters are among the largest structures in the universe. They are vast collections of galaxy clusters bound together by gravity. These structures span hundreds of millions of light years and contain thousands of galaxies. Voids, in contrast, are immense regions with very few galaxies. They are the large, empty spaces between superclusters. Voids can be tens to hundreds of millions of light years across, making them some of the largest features in the universe. The distribution of superclusters and voids forms a cosmic web. This web-like structure is a key feature of the large-scale universe. Filaments of dark matter and galaxies connect the dense regions of superclusters surrounding the vast voids. Superclusters contain a mix of galaxy types: spiral, elliptical, and irregular galaxies. All exist within these structures. The interactions between galaxies in superclusters can lead to merges, and the formation of new stars, the formation of superclusters, is influenced by dark matters. Gravitational pull helps bind clusters together into these massive structures. Over time, superclusters grow by attracting more galaxies, and clusters voids are created by the expansion of the universe and the gravitational influence of superclusters. As matter is pulled into superclusters, it leaves behind these empty regions. Voids represent the areas where gravitational forces are weaker. Studying superclusters and voids helps astronomers understand the distribution of matter in the universe. Observations reveal the intricate patterns of the cosmic web. These patterns provide clues about the nature of dark matter and the history of cosmic structure formation. The Sloan Digital Sky Survey and other large-scale surveys have mapped the distribution of superclusters and voids. These maps show the detailed structure of the universe on the largest scales. They help test theories of cosmology and the behavior of dark matter. Superclusters can influence the motion of galaxies within them. The gravitational forces within these structures can affect galaxy orbits and interactions. This dynamic environment leads to the evolution of galaxies over time. Voids are not completely empty, but contain some gas and a few galaxies. The galaxies within voids are often isolated and can evolve differently from those in denser regions. These isolated galaxies provide a unique laboratory for studying galaxy evolution. The study of superclusters and voids also provides insights into the expansion of the universe. The distribution of these structures is influenced by dark energy, which drives the accelerated expansion. Analyzing their distribution helps refine models of dark energy. Superclusters are often home to massive galaxy clusters, which can be observed in various wavelengths. X-ray observations reveal the hot gas within clusters, while optical and radio observations show the distribution of galaxies and dark matter. The interaction between superclusters and voids creates a dynamic cosmic environment. R flows along the filaments of the cosmic W, feeding superclusters and leaving behind expanding voids. This flow of matter shapes the large-scale structure of the universe. Understanding the relationship between superclusters and voids helps piece together the history of cosmic evolution. These structures trace the growth of the universe, from its early moments to the present day. Their study provides a comprehensive view of the cosmos superclusters and voids, are key components of the universe's large-scale structure. They reveal the distribution of matter and the influence of dark matter and dark energy. Studying these immense structures helps us understand the fundamental processes that shape the universe. The cosmic web is the large-scale structure of the universe, consisting of vast filaments of galaxies and dark matter. These filaments connect dense regions like galaxy clusters and superclusters, creating a complex network. The spaces between these filaments are the voids, which contain few galaxies. This web-like structure was formed by the gravitational pull of dark matter. As the universe expanded, dark matter clumped together, pulling regular matter along with it. These clumps grew over time, forming the filaments and nodes of the cosmic web. Galaxies and clusters are not randomly distributed, but are found along the filaments of the cosmic web. These filaments stretch across hundreds of millions of light years, creating a vast and intricate pattern. The nodes where filaments intersect are where galaxy clusters and superclusters are located. The cosmic web structure can be observed through large-scale galaxy surveys. These surveys map the distribution of galaxies, revealing the filamentary patterns. The Sloan Digital Sky Survey is one example that has provided detailed maps of the cosmic web. Dark matter is the backbone of the cosmic web. Its gravitational influence shapes the distribution of galaxies and gas. Although dark matter is invisible, its presence is inferred from its gravitational effects on visible matter. The cosmic microwave background radiation provides clues about the early stages of the cosmic web. Tiny fluctuations in the CMB reflect the initial density variations that grew into the large-scale structures we see today. These fluctuations were amplified by gravity over billions of years. Computer simulations of the universe's evolution help scientists understand the formation of the cosmic web. These simulations start with the initial conditions of the early universe and model the effects of gravity on dark matter and regular matter. The results closely match the observed structure of the universe. The cosmic web influences the formation and evolution of galaxies. Galaxies form and evolve along the filaments where gas and dark matter are most concentrated, the interaction between galaxies and the cosmic web shapes their properties and growth. The flow of gas along the filaments feeds galaxy formation. Gas moves from the voids into the filaments where it cools and co-endens to form new stars. This process continuously supplies galaxies with the material needed for star formation. The cosmic web also affects the motion of galaxies. Galaxies within filaments are pulled toward the nodes by gravity. This movement can lead to galaxy merges and interactions, further influencing galaxy evolution. The study of the cosmic web helps astronomers understand the large-scale distribution of matter. It provides insights into the behavior of dark matter and the effects of dark energy. The structure of the cosmic web is a crucial aspect of cosmological models. The cosmic web's influence extends to the distribution of hot gas in the universe. X-ray observations reveal that gas is concentrated in the filaments and nodes, heated by the gravitational collapse of matter. This hot gas emits X-rays, which can be detected by space telescopes. Understanding the cosmic web also helps explain the distribution of galaxy types. Different environments within the web lead to the formation of different types of galaxies. For example, elliptical galaxies are more common in dense cluster environments, while spiral galaxies are found along the filaments. The cosmic web is not static, but evolves over time. As the universe expands, the web structure becomes more pronounced. The filaments grow thicker, and the voids become emptier. This evolution is driven by the interplay between gravity and the expansion of the universe. Studying the cosmic web provides a comprehensive view of the universe's structure and evolution. It reveals how galaxies and clusters are interconnected and how they evolve within the larger cosmic framework. The cosmic web is a fundamental aspect of the universe's architecture, shaping its history and future. The life cycle of stars begins with the gravitational collapse of a gas cloud. This cloud, primarily composed of hydrogen contracts under gravity, forming a protostar. As the protostar continues to collapse, its core temperature rises. When the core temperature reaches about 10 million degrees, nuclear fusion begins. Hydrogen atoms fuse to form helium, releasing vast amounts of energy. This marks the birth of a new star entering the main sequence phase of its life. During the main sequence phase, a star fuses hydrogen into helium in its core. This phase can last for millions to billions of years, depending on the star's mass. The star remains stable, with the outward pressure from F fusion balancing the inward pull of gravity. As a star exhausts its hydrogen fuel, its core contracts, and heats up. The outer layers expand, and the star becomes a red giant. For stars like the Sun, this phase lasts for about 1 billion years. In the red giant phase, helium fusion begins in the core. Helium atoms fuse to form carbon and oxygen. For more massive stars, fusion can continue to create heavier elements up to iron. Once helium is exhausted, the core contracts again. Low-mass stars shed their outer layers, forming a planetary nebula, while the core becomes a white dwarf. A white dwarf slowly cools and fades over time. For massive stars, the fusion process continues until iron forms in the core. Ion fusion does not produce energy, leading to core collapse. This collapse triggers a supernova explosion, dispersing heavy elements into space. The remnants of a supernova can form a neutron star or a black hole. Neutron stars are incredibly dense, composed mostly of neutrons. If the core's mass is sufficient, it collapses further to form a black hole. Supernovae play a crucial role in enriching the interstellar medium with heavy elements. These elements are necessary for the formation of planets in life. The SH-OC waves from supernovae can also trigger the formation of new stars. Stars in binary systems can have different evolutionary paths. If one star becomes a white dwarf, it can accrete material from its companion. This can lead to novae or even type E supernovae, depending on the amount of accreted material. The end states of stars contribute to the diversity of stellar remnants in the galaxy. White dwarfs, neutron stars, and black holes each have unique properties and influence their surroundings in different ways. These remnants can be observed in various wavelengths. The of a star determines its life cycle. Massive stars have shorter, more violent lives, ending in supernova. Low-mass stars, like the Sun, have longer, more stable lives, ending as white dwarfs. The study of stellar life cycles provides insights into the processes that govern the universe. Understanding how stars form, evolve, and die helps explain the distribution of elements and the dynamics of galaxies. Stellar evolution is a fundamental aspect of astrophysics. Stellar nurseries, regions of active star formation, offer glimpses into the early stages of stellar life cycles. Observations of these regions reveal how stars form from collapsing gas clouds. They are crucial for understanding the initial conditions of star formation. Overall, the life cycle of stars is a complex interplay of gravity, nuclear fusion, and stellar dynamics, from birth in stellar nurseries to death as white dwarfs, neutron stars, or black hole stars undergo dramatic changes. Their life cycles shape the universe, influencing everything from galaxy formation to the creation of planets. The formation of heavy elements, also known as nucleosynthesis, occurs primarily in stars during the main sequence phase. Stars fuse hydrogen into helium in their cores. This process continues until the star exhausts its hydrogen supply. In more massive stars, after hydrogen is depleted, the core contracts and heats up. Helium fusion begins, creating heavier elements such as carbon and oxygen. These stars can undergo successive stages of fusion, producing elements up to ion. Ion is the heaviest element formed through fusion in stellar cores. Fusion reactions involving iron do not release energy, which leads to the collapse of the star's core. This collapse triggers a supernova explosion, dispersing heavy elements into space. Supernovae are critical for the formation of elements heavier than ion. During a supernova explosion, immense pressures and temperatures enable the rapid capture of neutrons by atomic nuclei. This process, known as the R process, creates many of the heaviest elements. Neutron star mergers also contribute to the formation of heavy elements. When two neutron stars collide, they produce heavy elements through rapid neutron capture. These mergers are thought to be significant sources of elements like gold and platinum. The elements formed in stars and supernova are scattered throughout the galaxy. This material enriches the interstellar medium, providing the building blocks for new stars, planets, and ultimately life. The distribution of these elements traces the history of stellar processes. Stars play a crucial role in the chemical evolution of the universe. Each generation of stars creates and disperses heavy elements, gradually enriching the galaxy. This process is ongoing, shaping the composition of future stars and planetary systems. The presence of heavy elements in young stars and planets indicates multiple generations of stellar evolution. The Sun, for example, contains heavy elements from previous supernova, suggesting it formed in an already enriched environment. The study of heavy element formation provides insights into the life cycles of stars. By analyzing the elemental composition of stars and stellar remnants, scientists can infer the processes that occurred during their lifetimes. This helps piece together the history of stellar nucleosynthesis. Heavy elements are essential for the development of planets, and life elements like carbon, nitrogen, and oxygen are critical for biological processes. The availability of these elements in planetary systems is a direct result of stellar nucleosynthesis. The detection of heavy elements in distant galaxies reveals the universality of these processes. Observations show that heavy elements are present even in the earliest galaxies, indicating that star formation and supernova were already occurring. Advanced telescopes and spectroscopic techniques allow astronomers to study the distribution of heavy elements in the universe. These observations help refine models of stellar evolution and nucleosynthesis. They also provide clues about the origins of cosmic structures. The formation of heavy elements is not limited to stars' processes like cosmic ray spallation, where high-energy particles collide with atomic nuclei, can also produce certain elements. These processes contribute to the overall chemical enrichment of the universe. Understanding the formation of heavy elements helps scientists explore the origins of the elements found on Earth. The elements in our planet were formed in previous generations of stars, highlighting the interconnectedness of cosmic and planetary evolution. Overall, the formation of heavy elements is a vital aspect of the universe's evolution. It connects the life cycles of stars with the chemical composition of galaxies and planets. Studying these processes reveals the dynamic and ongoing nature of cosmic nucleosynthesis. Supernovae are the explosive deaths of massive stars. These cataclysmic events release vast amounts of energy and light, briefly outshining entire galaxies. Supernova play a crucial role in the cosmic cycle of matter. The core collapse of a massive star triggers a supernova when the core's nuclear fuel is exhausted. It can no longer support the star against gravity. The core collapses, and the outer layers are violently ejected. This explosion disperses heavy elements into the surrounding space. Elements like iron, gold, and uranium are created in the intense conditions of a supernova. These elements enrich the interstellar medium, contributing to the formation of new stars and planets. Supernovae also release shock waves that compress nearby gas clouds. This compression can trigger the collapse of these clouds, leading to new star formation. In this way, supernova drive the cycle of star birth and death. There are two main types of supernova, type 1 and type 2. Type Y supernova occur in binary systems when a white dwarf accumulates material from a companion star. Type 2 supernova result from the core collapse of massive stars. Type A supernova are particularly important as standard candles in cosmology. Their consistent brightness allows astronomers to measure distances to far-away galaxies. These measurements are crucial for determining the expansion rate of the universe. Supernova remnants, the leftovers of these explosions, are fascinating objects. They consist of expanding shells of gas and dust, often forming beautiful and complex structures. These remnants continue to influence their surroundings long after the initial explosion. The Crab Nebula is one of the most famous supernova remnants. It was created by a supernova observed in 1054 AD. Today, the nebula is a source of valuable data about the aftermath of supernova explosions. Supernova can also impact the evolution of galaxies by injecting energy and heavy elements into the interstellar medium. They influence star formation rates and the chemical composition of galaxies. This feedback mechanism is a key aspect of galactic evolution. The study of supernova provides insights into the life cycles of stars. By observing supernova in different stages, astronomers can learn about the processes leading up to the explosion and the subsequent dispersal of elements. Supernovae are also sources of cosmic rays. These high-energy particles travel through space, sometimes reaching Earth. Cosmic rays can influence the chemistry of planetary atmospheres and contribute to space, whether the light from supernova can reveal much about the universe. Spectroscopic analysis of supernova light can identify the elements present in the explosion. This information helps scientists understand the nucleosynthesis that occurs during these events. The detection of supernova in distant galaxies helps astronomers map the history of star formation. By studying the frequency and distribution of supernova, scientists can infer the star formation rates in different regions of the universe. Supernovae are essential for creating the elements necessary for life. Without these explosive events, the universe would lack many of the heavy elements found in planets and living organisms. Supernovae thus play a critical role in the chemistry of life. Overall, supernova are dramatic and influential events in the universe. They drive the cosmic cycle of matter, contribute to star and planet formation, and help astronomers measure and understand the cosmos. Studying supernova enhances our knowledge of stellar evolution and the dynamic processes that shape the universe. The formation of neutron stars and black holes is a dramatic endo for massive stars. When a star exhausts its nuclear fuel, its core collapses under gravity. The outcome of this collapse depends on the mass of the core. For cores with masses between about 1, 4, and 3 times that of the Sun, the collapse leads to the formation of a neutron star. Neutron stars are incredibly dense, with a mass similar to the Sun's, but a diameter of only about 20 km. They are composed mostly of neutrons in the core of a collapsing star. Protons and electrons combined to form neutrons, releasing neutrinos in the process. This neutron-rich core resists further collapse due to neutron degeneracy pressure, which balances the inward pull of gravity. Neutron stars have extreme properties, including intense magnetic fields and rapid rotation rates. Some neutron stars, known as pulsars, emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space, creating a pulsating effect. If the core's mass exceeds about 3 solar masses, neutron degeneracy pressure cannot halt the collapse. The core continues to collapse into an infinitely dense point known as a singularity, forming a black hole. Black holes have gravitational field so strong that not even light can escape the boundary surrounding a black hole is called the event horizon. Within this region, the escape velocity exceeds the speed of light. The event horizon marks the point of no return beyond which nothing can escape the black hole's gravitational pull. The formation of a black hole is often accompanied by a powerful supernova explosion. This explosion expels the outer layers of the star into space, enriching the interstellar medium with heavy elements. The remnant core becomes the black hole. Black holes are detected through their interactions with nearby matter. As material falls into a black hole, it heats up and emits X-rays, which can be observed by telescopes. These emissions provide indirect evidence of the presence of black holes. Neutron stars and black holes play significant roles in the dynamics of galaxies. They can influence the motion of nearby stars and gas clouds in binary systems. They can accrete material from a companion star, leading to various high-energy phenomena. Neutron stars and black holes can also merge with other compact objects. These mergers release gravitational waves, ripples in space-time, that travel at the speed of light. Observations of gravitational waves provide insights into the properties of these exotic objects. The study of neutron stars and black holes help scientists understand the extreme conditions of matter and gravity. These objects are laboratories for testing theories of general relativity and nuclear physics. They reveal the behavior of matter under intense gravitational fields. Observations of neutron stars and black holes continue to challenge and refine our understanding of physics. The discovery of unexpected phenomena, such as fast radio bursts from neutron stars, opens new areas of research and exploration. Black holes, especially supermassive ones at the centers of galaxies, influence the formation and evolution of galaxies. The gravitational pull can shape the orbits of stars and affect the distribution of gas and dust. They also play a role in regulating star formation. Neutron stars and black holes represent the final stages in the life cycles of massive stars. Their formation marks the culmination of nuclear fusion processes that began in the star's core. Studying these objects helps complete the story of stellar evolution. Overall, neutron stars and black holes are fascinating and mysterious remnants of stellar evolution. Their extreme properties and powerful effects on their surroundings make them key objects of study in astrophysics, understanding their formation. Behavior enhances our knowledge of the universe's stellar nurseries, are regions where new stars are born. These areas rich in gas and dust are often found in the arms of spiral Jesus. They are also known as molecular clouds due to their dense concentrations of molecules like hydrogen. The process of star formation begins when regions within these clouds collapse under our gravity. As the cloud collapses, it fragments into clumps, each of which can form one or more new stars. This collapse increases the temperature and pressure within the clumps. Protostars form. In the centers of these collapsing clumps, as material continues to fall inward, the protostar grows in mass and heats up eventually. The core temperature becomes high enough for nuclear fusion to begin, marking the birth of a new star. Stellar nurseries are often hidden from view by thick clouds of dust. However, infrared and radio telescopes can penetrate these clouds, revealing the formation processes within observations in these wavelengths provide crucial insights into the early stages of star formation. The birth of stars within stellar nurseries is often accompanied by the formation of protoplanetary disks. These disks of gas and dust surround the young stars and are the birthplaces of planets. The material in these disks coalesces over time to form planetary systems. Massive stars formed in stellar nurseries can influence the formation of other stars. Their intense radiation and stellar winds can compress nearby gas clouds, triggering further star formation. This process is known as triggered star formation. The Orion Nebula is a well-known stellar nursery, visible to the naked eye. It is a rich region of star formation containing hundreds of young stars in various stages of development. Observations of the Orion Nebula provide a wealth of information about stellar nurseries. The process of star formation is a balance between gravity and pressure. While gravity pulls material inward to form stars, thermal pressure and magnetic fields can resist the collapse. Understanding this balance is key to studying star formation. Stellar nurseries are dynamic environments with complex interactions between gas, dust, and young stars. Turbulence within the clouds can create regions of varying density, influencing where and how stars form. These interactions are subjects of active research in astrophysics. The initial mass function describes the distribution of star masses in a stellar nursery. It reveals that most stars form with relatively low masses, while massive stars are rarer. This distribution affects the evolution of star clusters and galaxies. Stars formed in stellar nurseries often remain bound together in clusters over time. These clusters can disperse as stars drift apart. However, the gravitational pull within the cluster can keep many stars bound together for millions of years. The formation of stars in stellar nurseries also contributes to the chemical evolution of galaxies as stars form and later die. They enrich the interstellar medium with heavy elements. This ongoing cycle influences the composition of future generations of stars. Stellar nurseries vary in size and activity. Some are relatively small, forming a few stars, while others, like the Kina Nebula, are vast regions producing thousands of stars. The diversity of these nurseries provides a broad range of environments for studying star formation. Understanding stellar nurseries helps astronomers learn about the conditions necessary for star formation. These regions are crucial for understanding the origins of stars and planetary systems. Observations and simulations continue to advance our know of these cosmic birthplaces. Overall, stellar nurseries are the cradles of star formation. They represent the initial stages of stellar life cycles, where gas and dust transform into new stars and planets. Studying these regions is essential for understanding the processes that shape the universe. The formation of the solar system began about 6 billion years ago. It started within a giant molecular cloud composed of gas and dust. A region of this cloud collapsed under its own gravity, forming a protostar that would become the Sun. As the protostar formed, the remaining material flattened into a rotating protoplanetary disk. This disk contained all the elements that would eventually form the planets, moons, asteroids, and comets. The Sun began to shine as nuclear fusion ignited in its core. In the protoplanetary disk, particles of dust, ice collided and stuck together, forming larger and larger clumps. Over time, these clumps grew into planet symbols which are the building blocks of planets. The planetesimals continued to collide and merge, forming protoplanets closer to the young sun. The intense heat caused volatile compounds to evaporate, leaving behind rocky material. This led to the formation of the terrestrial planets Mercury, Venus, Earth, and Mars. These planets are composed primarily of rock and metal. Farther from the sun, beyond the frost line, temperatures were low enough for ices to remain solid, ID. This allowed the formation of gas giants and ice giants Jupiter and Saturn. The gas giants accumulated massive amounts of hydrogen and helium. Uranus and Neptune. The ice giants formed from heavier ice. The formation of Jupiter had a significant impact on the solar system. Its immense gravity influenced the orbits of nearby planetesimals, ejecting some from the solar system and preventing others from forming into planets. This process helped shape the asteroid belt. As the planets formed, they cleared their orbits of debris. Smaller bodies that did not accrete into planets became asteroids and comets. The asteroid belt between Mars and Jupiter is a remnant of these planetesimals that never formed into a planet. The Kuiper belt and the Oort cloud are regions filled with icy bodies. The Kuiper belt lies beyond Neptune and is the source of many short-period comets. The Oort cloud is a distant spherical shell surrounding the solar system, home to long-period comets during the late stages of the solar system's formation. The young planets experienced heavy bombardment. This period, known as the late heavy bombardment, was characterized by frequent collisions with leftover planetesimals. These impacts played a role in shaping the surfaces of the planets and moons, and the formation of the moon is believed to be the result of a giant impact. A Mars-sized body named Theia collided with the earlier Earth, ejecting a large amount of material into orbit. This debris eventually coalesced to form the moon. The early solar system was a chaotic place with frequent collisions and dynamic interactions. Over time, the planet settled into more stable orbits. The gravitational interactions between the planets helped to clear the solar system of much of its remaining debris. The study of meteorites provides valuable insights into the solar system's formation. These ancient rocks are remnants of the Earth's early solar system, preserving information about its initial conditions and processes meteorites contain clues about the composition and age of the solar system. The discovery of exoplanets around other stars has expanded our understanding of planetary formation. By comparing our solar system to others, scientists can identify common processes and unique features. This comparative study helps refine theories of planet formation. The formation of the solar system set the stage for the development of life on Earth. The delivery of water and organic compounds by comets and asteroids may have been crucial for the emergence of life. The stable environment of the solar system has allowed life to thrive for billions of years. Overall, the formation of the solar system was a complex and dynamic process. It involved the interplay of gravity collisions and the influence of the young sun. Studying this process provides insights into the origins of our own planetary system and the formation of planets around other stars. The birth of the sun began within a giant molecular cloud about 4.6 billion years ago. This cloud, composed primarily of hydrogen and helium, contained traces of heavier elements from previous generations of stars. A disturbance, possibly a nearby supernova explosion, triggered the collapse of a region within the cloud. As the region collapsed, it formed a dense core that continued to draw in material from its surroundings. The core heated up due to the conversion of gravitational energy into thermal energy. This growing protostar was the sun over time. The protostar's temperature and pressure increased until nuclear fusion began in its core. Hydrogen atoms fused to form helium, releasing enormous amounts of energy. This process marked the transition from a protostar to a main sequence star, the birth of the sun. The onset of nuclear fusion generated an outward pressure that balanced the inward pull of gravity. This equilibrium, known as hydrostatic equilibrium, stabilized the sun. The intense energy output from fusion caused the surrounding gas and dust to be blown away, clearing the immediate vicinity. The young sun was more active than it is today. It emitted powerful solar winds and intense ultraviolet radiation. These solar winds helped shape the solar system, pushing away lighter elements and contributing to the formation of the planetary orbit. The sun's birth also influenced the composition of the planets. The intense heat from the young sun caused volatile compounds to evaporate in the inner solar system, leading to the formation of rocky terrestrial planets. In contrast, the cooler outer regions allowed gas giants to form. As the sun entered the main sequence phase, it settled into a period of stability that has lasted billions of years. During this time, it has steadily fused hydrogen into helium, providing the energy that supports life on Earth. This stable phase is expected to continue for several billion more years. The sun's magnetic field, generated by its rotating convective interior, played a crucial role in shaping the early solar system. Magnetic activity drove solar flares and coronal mass ejections, which influenced the environment of the young planets. The early sun was part of a stellar nursery, a region where many stars formed from the same molecular cloud. These sibling stars have since dispersed throughout the Milky Way, but studying them provides clues about the conditions in which the sun was born. The discovery of ancient meteorites on Earth has provided valuable information about the sun's formation. These meteorites contain isotopic signatures that date back to the early solar system, offering GHTS into the processes that occurred during the sun's birth. And the sun's formation was a critical event in the history of the solar system. It provided the energy needed to drive chemical reaction on the early Earth, leading to the emergence of life. The stable environment created by the sun's consistent energy output has allowed life to flourish. The study of other young stars in our galaxy helps scientists understand the sun's early years. Observations of protostars and young main sequence stars reveal the processes involved in stellar formation and evolution. These studies help refine models of the sun's birth and early development. As the sun continues its journey through the main sequence, it will eventually exhaust its hydrogen fuel. This process will lead to significant changes in the sun's structure and behavior, marking the end of its current stable phase. However, for now, the sun remains a steady source of energy for our solar system. The birth of the sun was a transformative event that set the stage for the development of the planet's moons and other objects in the solar system. Understanding this process helps scientists piece together the history of our cosmic neighborhood, and T, he conditions that led to the emergence of life on Earth. The accretion of planets began within the protoplanetary disk surrounding the young sun. This disk, composed of gas, dust, and ice, provided the raw materials for planet formation. Tiny particles within the disk collided and stuck together, forming larger and larger clumps. These clumps grew into planetesimals, the building blocks of planets, through a process called runaway growth. Planetesimals attracted more material, increasing in size rapidly. This stage marked the beginning of planetary accretion in the inner solar system, where temperatures were high. Her planetesimals formed from rocky and metallic materials. These materials had higher melting points and could withstand the heat closer to the sun. This led to the formation of the terrestrial planets farther out in the cooler regions of the disk. Planetesimals incorporated IES in addition to rock and metal. This allowed them to grow much larger, leading to the formation of the gas giants and ice giants Jupiter and Saturn. Accumulated massive amounts of hydrogen and helium, while Uranus and Neptune collected more IES and less gas. As planetesimals grew, their gravity influenced nearby particles. They cleared their orbits of smaller debris, sweeping up material and growing even larger. This process helped define the distinct regions of the solar system. Collisions between planetesimals were common in the early solar system. Some collisions were destroy RVE, shattering bodies into smaller pieces. Others were constructive, merging bodies to form larger protoplanets. These dynamic interactions played a crucial role in shaping the planet. The process of accretion continued over millions of years. Gradually, the largest protoplanets became dominant, absorbing smaller bodies and clearing their orbital paths. This led to the formation of the planets we recognize today. The differentiation of planets occurred as they grew and heated up. Heavier materials sank to the center, forming cores, while lighter materials formed mantles and crusts. This differentiation resulted in the layered structures observed in the terrestrial planets' volcanic activity. On young planets, released gases from their interiors, contributing to the formation of atmospheres. Outgassing from volcanoes released water vapor, carbon dioxide, and other gases, shaping the early atmospheres of the planets in the outer solar system that the gas giant strong gravity allowed them to capture and retain thick atmospheres of hydrogen and helium. These massive planets also influenced the formation of moons and ring systems from the surrounding debris. The process of accretion also led to the formation of moons. Some moons form from the same material as their parent planets, while others were captured planetesimals. The diverse origins of moons add to the complexity of the solar system. Asteroids and comets are remnants of the planetesimal population. They provide valuable clues about the conditions in the early solar system. Studying these small bodies helps scientists understand the processes that led to planetary formation. The presence of water on Earth and other planets is a result of accretion. Water-rich planetesimals and comets delivered water to the growing planets. This delivery of water was crucial for the development of life on Earth. The accretion process was influenced by the migration of planets. As planets formed, they interacted with the protoplanetary disks, causing them to migrate inward or outward. These migrations affected the distribution and final arrangement of the planets. Understanding the accretion of planets provides insights into the formation and evolution of the solar system. By studying other planetary systems, scientists can compare them to our own refining theories of planet formation. The process of accretion is a fundamental aspect of planetary science, revealing the origins of the diverse worlds that orbit the Sun. The emergence of a habitable environment on Earth began with the formation of its atmosphere, and oceans' volcanic activity released gases like water vapor, carbon dioxide, and nitrogen into the atmosphere. This outgassing process contributed to the development of a thick, insulating atmosphere. Water vapor in the atmosphere condensed as the planet cooled, leading to the formation of oceans. These bodies of water covered much of the Earth's surface, providing a crucial ingredient for life. The oceans also played a role in regulating the planet's temperature. The presence of liquid water created conditions favorable for chemical reactions necessary for life. Early Earth's environment was dynamic, with frequent volcanic eruptions, lightning, and intense ultraviolet radiation. These conditions may have driven the formation of complex organic molecules. The Earth's magnetic field, generated by its rotating molten iron core, protected the atmosphere from solar wind erosion. This magnetic shield preserved the atmosphere's integrity, allowing it to support life. The magnetic field continues to play a crucial role in maintaining a habitable environment. Plate tectonics contributed to the recycling of nutrients and the stabilization of the climate. The movement of tectonic plates led to the formation of continents and ocean basins. Volcanic activity associated with plate boundaries released essential minerals and gases. The carbon cycle involving the exchange of carbon dioxide between the atmosphere. Here, oceans and rocks regulated Earth's climate. Photosynthesis by early microbial life converted carbon dioxide into oxygen, gradually increasing atmospheric oxygen levels. This oxygenation was crucial for the development of complex life. Stromatolites, layered structures formed by microbial communities, provide some of the earliest evidence of life. These ancient fossils, dating back over 3 billion years, show that microbial life thrived in shallow sunlit waters. Stromatolites played a role in oxygenating the atmosphere. The ozone layer, formed by the accumulation of oxygen in the atmosphere, provided protection from harmful ultraviolet radiation. This layer allowed life to colonize the land, expanding the habitable environment beyond the oceans. The development of the ozone layer was a significant milestone in Earth's history. The emergence of a stable climate was essential for sustaining life. Earth's distance from the sun, combined with its atmospheric composition, created a balance that allowed liquid water to persist. This stable environment supported the continuous evolution of life. The Earth's biosphere, the global sum of all ecosystems, became a self-regulating system. Interactions between living organisms and their environment maintain the conditions necessary for life. The biosphere complexity increased over time, leading to greater biodiversity. The evolution of plants played a critical role in shaping the habitable environment. Photosynthetic plants increased oxygen levels and contributed to the formation of soil. Plant roots stabilize the soil, reducing erosion and enhancing the cycling of nutrients. The development of a diverse range of habitats, from deep oceans to high mountains provided niches for various forms of life. This diversity promoted the evolution of complex ecosystems. ECH habitat offered unique opportunities and challenges for living organisms. The presence of a moon resulting from a massive impact with Earth helped stabilize the planet's axial tilt. This stabilization led to more consistent seasons and climate patterns. The moon's gravitational influence also contributed to the regulation of tides, impacting coastal ecosystems throughout Earth's history. Mass extinctions have periodically reshaped the biosphere. These events, caused by factors like volcanic eruptions and asteroid impacts, created opportunities for new forms of life to emerge. Each extinction event led to a burst of evolutionary innovation. Overall, the emergence of a habitable environment on Earth was a complex interplay of geological, atmospheric, and biological processes. These processes transform the planet from a lifeless rock into a thriving, diverse biosphere. Understanding these factors helps scientists search for habitable environments on other planets. Theories of life origin explore how life began on Earth from non-living matter. One prominent hypothesis is the primordial soup theory. It suggests that life started in a soup of organic molecules, possibly in the early Earth's oceans. This theory was supported by the Miller-Urey experiment in the 1950s. They simulated early Earth conditions and produced amino acids, the building blocks of proteins, from simple chemicals. This experiment showed that organic molecules could form under prebiotic conditions. Another hypothesis is the deep sea hydrothermal vent theory. It proposes that life originated near hydrothermal vents on the ocean floor. These vents provide heat and a rich chemical environment which could foster the synthesis of organic molecules. The panspermia hypothesis suggests that life might have originated elsewhere in the universe and was brought to Earth by comets or meteorites. This theory posits that microbial life could survive the harsh conditions of space and initiate life upon reaching Earth. RNA world hypothesis suggests that RNA, a molecule capable of both storing genetic information and catalyzing chemical reactions, was the first molecule of life. RNA could replicate itself and evolve, leading to the development of more complex life forms metabolism. First hypothesis posits that metabolic networks, or sets of chemical reactions, predated genetic information. Simple metabolic pathways could have formed spontaneously. A and D driven the production of organic molecules necessary for life. Clay mineral theory suggest that life might have originated on the surfaces of clay minerals. These minerals could catalyze the formation of organic molecules and provide a template for the first genetic material. This theory combines elements of both metabolism and genetic theories. The ion-sulfur world hypothesis proposes that life began on the surface of ion and nickel sulfide minerals at high temperatures. These conditions could drive the formation of organic molecules and support the earliest forms of metabolism. Some theories suggest that life could have started in ice-cold environments, might concentrate organic molecules, promoting the formation of complex structures. Ice could also protect these molecules from damaging UV radiation. Lipid world hypothesis posits that life began with self-replicating lipid structures, which could form cell-like compartments. These compartments could concentrate organic molecules and facilitate the development of metabolic pathways and genetic material. The Kavod theory suggests that life began in cultivates, which are droplets of organic molecules surrounded by water. Cultivates can concenter 8 organic molecules and create microenvironments that promote chemical reactions. Hydrothermal crater lakes are another proposed site for the origin of life. These lakes, formed by volcanic activity, provide heat, water, and a rich chemical environment. They could support the formation of organic molecules and early life forms. The electric spark hypothesis suggests that lightning or other electrical discharges could have provided the energy needed to synthesize organic molecules from simple gases in the early Earth's atmosphere. This hypothesis builds on the results of the Miller-Urey experiment. Polymerization on mineral surfaces theory suggests that minerals could catalyze the formation of long-chain molecules like proteins and nucleic acids. These surfaces could also help organize and protect these molecules, facilitating the development of life. Understanding the origin of life remains one of the most intriguing questions in science. Each theory provides a different perspective on how life might have begun, and ongoing research continues to explore these possibilities. Discovering the true origin of life could have profound implications for our understanding of biology and the potential for life elsewhere in the universe. The first simple organisms on Earth were likely prokaryotes, single-celled organisms. Without a nucleus, these early life forms appeared around 5 to 4 billion years ago. Fossil evidence, such as stromatolites, provides clues about these ancient microbes. These prokaryotes included bacteria and archaea. They thrived in a variety of environments, from hot hydrothermal vents to shallow coastal areas. Their metabolic diversity allowed them to exploit different energy sources. Some of the earliest prokaryotes were likely chemoautotrophs. These organisms obtained energy by oxidizing inorganic molecules such as hydrogen sulfide or iron. This metabolism allowed them to thrive in environments devoid of sunlight. Photosynthetic bacteria like cyanobacteria appeared later. They used sunlight to convert carbon dioxide and water into organic compounds, releasing oxygen as a byproduct. This process gradually increased the oxygen levels in Earth's atmosphere. The rise of oxygen from photosynthesis had a profound impact on the planet. It led to the Great Oxygenation Event around 4 billion years ago. This increase in atmospheric oxygen allowed for the evolution of aerobic respiration. Aerobic respiration provided a more efficient way to produce energy. It enabled the evolution of more complex and energy-demanding life forms. This metabolic shift paved the way for the development of multicellular organisms. The simplicity of early prokaryotes belied their biochemical sophistication. They possessed a variety of metabolic pathways and mechanisms for adapting to changing environments. These adaptations were crucial for their survival and proliferation. Horizontal gene transfer played a significant role in the evolution of these early organisms. This process allowed them to exchange genetic material, spreading beneficial genes across different species. It contributed to the rapid evolution of metabolic capabilities. Biofilms were another important adaptation of early prokaryotes. These communities of microorganisms adhered to surfaces and protected themselves with a self-produced matrix biofilms, provided stability and protection in harsh environments. The fossil record of these early organisms is sparse, but telling microfossils and chemical signatures in ancient rocks provide evidence of their existence. These findings help scientists reconstruct the conditions and processes of early life on Earth. The transition from simple to more complex life involved the development of eukaryotic cells, which appeared around 1.6 to 2 billion years ago, have a nucleus and other organelle. This cellular complexity allowed for greater specialization and multicellularity. Endosymbiosis played a key role in the evolution of eukaryotes. This process involved the incorporation of one organism into another, leading to the formation of organelle like mitochondria and chloroplasts. These symbiotic relationships enhanced cellular efficiency and diversity. The study of extremophiles, modern prokaryotes that live in extreme environments, provides insights into early life. These organisms thrive in conditions similar to those of early Earth, such as high temperatures, acidity, or salinity. Their adaptations offer clues about the resilience and versatility of ancient life forms. Understanding the first simple Auran organisms helped scientists explore the potential for life on other planets. If life could arise and thrive in the extreme conditions of early Earth, it might also exist in similar environments elsewhere in the universe. This perspective guides the search for extraterrestrial life. The first simple organisms laid the foundation for all subsequent life on Earth. Their metabolic innovations, adaptability, and resilience set the stage for the evolution of more complex organisms. Studying these early life forms reveals the fundamental processes that drive life's diversity and persistence. The evolution of complex life began with the emergence of eukaryotic cells. These cells, with their nuclei and organelle, allowed for greater cellular specialization. This development was a key step towards multicellularity. Eukaryotic cells likely evolved through endosymbiosis. This process involved one cell engulfing another, leading to a symbiotic relationship. Mitochondria and chloroplasts in modern cells are thought to have originated this way. The transition to multicellularity allowed organisms to grow larger and more complex cells within. Multicellular organisms could differentiate into various types, performing specialized functions. This differentiation led to the development of tissues and organs. The first multicellular organisms were simple and consisted of a few cells. Over time, evolutionary pressures led to greater complexity. These pressures included predation, environmental changes, and competition for resources. The Cambrian explosion, around 541 million years ago, marked a rapid diversification of life forms. During this period, most major animal phyla appeared. Fossils from the Cambrian period show a wide variety of complex organisms. The development of hard parts such as shells and exoskeletons was a significant evolutionary advancement. These structures provided protection and support, allowing organisms to explore new ecological niches. This innovation is well documented in Cambrian fossils. Complex life forms developed various strategies for survival and reproduction. These included mobility s sensory organs and nervous systems, the ability to move and sense the environment provided significant evolutionary advantages. Plants began colonizing land around 470 million years ago. The evolution of vascular tissue allowed them to transport water and nutrients, enabling them to grow taller and thrive in diverse environments. This transition dramatically altered Earth's landscapes. The colonization of land by animals followed the plants. Arthropods were among the first to move onto land, followed by amphibians. The development of limbs and lungs facilitated this transition, allowing animals to exploit new habitats. The evolution of complex life also saw the rise of vertebrates. Vertebrates have a backbone which provides structural support and protects the spinal cord. This group includes fish, amphibians, reptiles, birds, and mammals. Reproduction evolved in complexity alongside other life processes. Sexual reproduction, with its genetic recombination, introduced greater genetic diversity. This diversity provided a rich substrate for natural selection to act upon the development of complex ecosystems. Followed the evolution of complex life forms. These ecosystems comprised various organisms interacting in intricate food webs, energy flow, and nutrient cycling became more sophisticated, supporting diverse communities. Mass extinctions periodically disrupted the evolution of complex life. These events wiped out significant proportions of Earth species, but also created opportunities for new forms to emerge. The aftermath of extinctions often led to bursts of evolutionary innovation. The rise of mammals and birds occurred after the extinction of the dinosaurs. These groups diversified to fill the ecological niches left vacant. Mammals, with their warm-blooded metabolism and complex brains, adapted to various environments. The evolution of complex life culminated in the development of humans, Homo sapiens, with their large brains and advanced cognitive abilities, have profoundly impacted the Earth. Understanding the evolution of complex life helps us appreciate the interconnectedness and fragility of life on our planet. The Cambrian explosion occurred around 541 million years ago and marked a significant diversification of life on Earth. During this period, most major animal phyla appeared. Fossils from this time show a wide variety of complex organisms. This event was characterized by the rapid evolution of many different body plans. Organisms developed hard parts like shells and exoskeletons, which are well preserved in the fossil record. These structures provided protection and support, allowing organisms to explore new ecological niches. The Cambrian explosion saw the emergence of complex sensory organs, eyes, and other sensory structures evolved, enhancing the ability of organisms to detect and respond to their environment. This increased sensory capability was a significant evolutionary advantage. Predation became a driving force during this period. The evolution of predators and prey led to an evolutionary arms race. Organisms developed various defensive and offensive adaptations, such as armor and specialized feeding appendages. The increase in oxygen levels in the oceans is thought to have contributed to the Cambrian explosion. Higher oxygen levels allowed for more efficient metabolism and greater energy production. This supported the development of larger and more complex organisms. The development of the genetic toolkit played a crucial role in the diversification of life. During the Cambrian explosion, regulatory genes controlled the development of different body plans, allowing for a wide range of morphological cal diversity. This genetic innovation facilitated the rapid evolution of new forms. The fossil record from the Cambrian period includes well-known sites like the Burgess Shale. These fossil beds contain exceptionally well-preserved specimens, providing detailed insights into the anatomy and diversity of Cambrian life. The Burgess Shale fossils reveal a rich tapestry of early animal life, soft-bodied organisms, which are less likely to fossilize, also thrive during the Cambrian explosion. Fossils of these organisms provide valuable information about the diversity of life forms that existed during this period. The preservation of soft tissues offers a more complete picture of early animal diversity. The Cambrian seas were teeming with life, including trilobites, brachiopods, and early arthropods. These creatures occupied various ecological niches, from bottom dwellers to free-swimming predators. The complexity of Cambrian ecosystems rivals that of modern marine environment. Hence, the explosion of life during the Cambrian period set the stage for future evolutionary developments. Many of the body plans that emerged during this time are still present in modern animal phyla. The Cambrian explosion laid the foundation for the diversity of life we see today. The causes of the Cambrian explosion are still debated among scientists. Various hypotheses include changes in the environment, genetic innovations, and ecological interactions. Understanding this event requires a multidisciplinary approach, combining geology, paleontology, and evolutionary biology. The rapid diversification of life during the Cambrian explosion challenges traditional views of gradual evolution. It suggests that under certain conditions, evolution can proceed at an accelerated pace. This has implications for understanding the dynamics of evolutionary change. Studying the Cambrian explosion helps scientists understand the processes that drive major evolutionary transitions. It provides insights into how life can diversify rapidly in response to new opportunities and challenges. This period is a key focus for research in evolutionary biology. The Cambrian explosion also has implications for the search for life on other planets. It demonstrates how quickly complex life can evolve under the right conditions. This knowledge can guide the search for extraterrestrial life and the interpretation of potential biosignatures. Overall, the Cambrian explosion was a pivotal event in the history of life on Earth. It marked the rapid emergence of complex multicellular organisms and set the stage for the subsequent evolution of animal life. Understanding this event provides crucial insights into the mechanisms of evolution and the history of life on our planet. Mass extinctions have profoundly shaped the course of life on Earth. These catastrophic events wiped out large numbers of species in relatively short periods. Each extinction event reset the evolutionary clock, allowing new life forms to emerge and diversify. The most well-known mass extinction occurred 66 million years ago, marking the end of the Cretaceous period. This event led to the extinction of the dinosaurs, paving the way for mammals to dominate the planet. The impact of an asteroid is widely believed to have triggered this extinction. Another significant extinction event was the Triassic extinction, occurring around 252 million years ago. It is the most severe known extinction, with over 90% of marine species and 70% of terrestrial vertebrates disappearing. Massive volcanic eruptions in Siberia are thought to have caused this die-off. The Avis Silurian extinction, about 444 million years ago, saw the loss of 85% of marine species. This event was likely caused by a short, severe ice age, followed by rapid warming. The resulting sea level changes and reduced oxygen levels devastated marine life. The late Devonian extinction, occurring around 360 million years ago, resulted in the loss of 70% of marine species. This prolonged event may have been caused by changes in sea levels, climate fluctuations, and possibly asteroid impacts. The Triassic-Jurassic extinction, about 2011 million years ago, wiped out around 80% of species. This event paved the way for the rise of dinosaurs. Volcanic activity associated with the opening of the Atlantic Ocean is a leading hypothesis. Is for this extinction. Mass extinctions have often been followed by periods of rapid evolutionary diversification. The extinction of dominant species creates ecological niches that new and surviving species can exploit. This process, known as adaptive radiation, leads to bursts of evolutionary innovation. The loss of biodiversity during mass extinctions has significant ecological impacts. Ecosystems lose complexity and resilience, and recovery can take millions of years. The surviving species often undergo dramatic changes in behavior and physiology to adapt to new conditions. Mass extinctions also have profound effects on the planet's geochemistry. The collapse of ecosystems alters carbon and nutrient cycles. For example, the end-Perian extinction led to the proliferation of bacteria that produce large amounts of hydrogen sulfide, further disrupting the environment. Studying past mass extinctions helps scientists understand the potential impacts of current biodiversity loss. Human activities are driving a sixth mass extinction, characterized by rapid species declines, habitat destruction. Learning from past events can inform conservation strategies. The fossil record provides critical evidence for understanding mass extinctions. It reveals patterns of species loss and recovery, helping to identify potential causes and consequences. Advances in dating techniques and paleo-environmental reconstructions enhance our understanding of these events. Mass extinctions highlight the interconnectedness of life and the environment. They show how changes in climate, sea levels, and other factors can ripple through ecosystems, affecting species survival. This perspective underscores the importance of maintaining environmental stability. The role of mass extinctions in shaping evolution cannot be overstated. They act as both destroyers and creators, eliminating entire lineages while allowing new ones to flourish. This dual role has driven the dynamic and ever-changing nature of life on Earth. Understanding mass extinctions provides insights into the resilience and adaptability of life. Despite the profound losses, life has repeatedly rebounded, evolving new forms and filling vacant ecological niches. This resilience is a testament to the enduring power of evolutionary processes. Overall, the impact of mass extinctions extends far beyond the immediate loss of species. These events have reshaped the trajectory of life on Earth. In influencing the evolution of ecosystems and the diversity of life forms. Studying them deepens our understanding of the past and helps us navigate the future. The fate of stars is determined by their mass. Low-mass stars, like the Sun, will eventually exhaust their hydrogen fuel and become red giants. They will shed their outer layers, creating a planetary nebula, while the core becomes a white dwarf. White dwarfs will gradually cool and fade over billions of years. They will eventually become cold, dark remnants known as black dwarfs. However, the universe is not old enough for any black dwarfs to exist. Yet, massive stars have a more dramatic fate. They end their lives in supernova explosions, ejecting their outer layers into space. The core collapses to form either a neutron star or a black hole, depending on its mass. Neutron stars are incredibly dense and can spin rapidly, emitting beams of radiation. As pulsars over time will slow down and cool, becoming faint and difficult to detect. Black holes, on the other hand, will continue to grow by accreting matter and merging with other black holes. Binary star systems can have complex fates if one star evolves into a white dwarf and its companion is close enough it can transfer material onto the white dwarf. This can lead to a supernova, if the white dwarf reaches a critical mass. Galaxies also evolve over time. Spiral galaxies can merge to form elliptical galaxies. These mergers can trigger bursts of star formation and alter the galaxy structures over billions of years. Galaxy interactions and mergers will continue to shape the universe. The Milky Way will eventually merge with the Andromeda galaxy. This event is predicted to occur in about 4-5 billion years. The resulting galaxy will be a large elliptical, sometimes called Mila or milk dromeda. The fate of the universe itself depends on its overall density and the nature of dark energy. If dark energy continues to drive the accelerated expansion, the universe will expand forever. This scenario is known as the Big Freeze or heat death. In the Big Freeze, galaxies will drift apart and star formation will cease. As the supply of gas is exhausted, stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation. Another possible fate is the Big Crunch. where the universe's expansion halts and reverses. This would lead to a collapse of all matter and energy back into a singularity. However, current observations suggest this scenario is less likely. The Big Rip is another hypothesis where dark energy's repulsive force increases over time. This would tear apart galaxies, stars, planets, and eventually atomic structures. The universe would end in a state of EXT, disintegration. Galactic evolution is influenced by dark matter, which makes up most of the universe's mass. Dark matter's gravitational effects help bind galaxies together and influence their interactions. The distribution of dark matter will play a role in the ultimate fate of galaxies. The study of cosmic background radiation provides insights into the universe's fate. Observations of the CMB reveal the universe's expansion history and its future trajectory. These studies help refine models of cosmic evolution, the fate of stars and galaxies is a fundamental question in astrophysics. Understanding these processes provides insights into the life cycle of the cosmos, each star's life, and each galaxy's evolution contribute to the ongoing story of the universe. Dark energy is a mysterious force driving the accelerated expansion of the universe. It makes up about 68% of the total energy content of the cosmos. The discovery of dark energy was one of the most significant developments in modern cosmology. In 1998, observations of distant supernova revealed that the universe's expansion was accelerating. This unexpected finding suggested the presence of an unknown energy component counteracting gravity. Dark energy was introduced to explain this phenomenon. Dark energy's exact nature remains unknown. It could be a property of space itself, described by Einstein's cosmological constant. Alternatively, it might be a dynamic field that changes over time, known as quintessence. The effects of dark energy are observed in the large-scale structure of the universe. It influences the growth of galaxy clusters and the distribution of galaxies. By studying these structures, scientists can learn more about dark energy's properties. The cosmic microwave background radiation provides clues about dark energy. Detailed measurements of the CNB's temperature fluctuations help constrain the amount of dark energy. These observatio NS are essential for understanding the universe's expansion, history, dark energy's repulsive force increases. As the universe expands, this means its influence grows over time, further accelerating the expansion. This behavior contrasts with gravitational forces, which weaken with distance. The accelerated expansion has profound implications for the universe's fate. If dark energy continues to dominate the universe, will expand forever in a big freeze. In this scenario, galaxies will drift apart and star formation will cease, leading to a cold, dark cosmos. Alternative models suggest different outcomes. The Big Rip hypothesis proposes that dark energy strength could increase, tearing apart galaxies' stars and eventually atomic structures. This catastrophic end would occur if dark energy's repulsive force grows without bounds. Observations of galaxy clusters help test dark energy theories. The distribution and behavior of these clusters provide insights into the balance between dark energy and gravity. Surveys like the Sloan Digital Sky Survey collect data crucial for these studies. Gravitational lensing is another tool for studying dark energy. It involves the bending of light by massive objects which can reveal the distribution of dark matter and dark energy. Precise measurements of lensing effects help constrain dark energy models. Future missions aim to probe dark energy with greater precision. The Euclid satellite and the Wide Field Infrared Survey Telescope first will map the universe in unprecedented detail. These missions will improve our understanding of dark energy's role in cosmic evolution. Theoretical physicists explore various explanations for dark energy. Some propose modifications to general relativity or new forms of matter. These theories aim to integrate dark energy into a coherent framework of fundamental physics. Understanding dark energy is one of the biggest challenges in cosmology. It requires a combination of observational, experimental, and theoretical approaches. Each new discovery brings us closer to unraveling this cosmic mystery. Dark energy research has broader implications for physics. It touches on fundamental questions about the nature of space-time and the universe's structure. Insights gained from studying dark energy could revolutionize our understanding of the cosmos. The study of dark energy and cosmic acceleration is a dynamic and evolving field. As new data and theories emerge, our picture of the universe continues to refine. The quest to understand dark energy is a testament to human curiosity and the drive to explore the unknown. One possible scenario for the end of the universe is the Big Freeze. In this scenario, the universe continues to expand forever. As galaxies move farther apart, stars will eventually burn out, and the cosmos will grow cold and dark. Another potential end is the Big Crunch. This scenario involves the universe's expansion halting and then reversing. All matter and energy would collapse back into a singularity, possibly leading to a new Big Bang. The Big Rip is a more extreme possibility. If dark energy's repulsive force increases over time, it could tear apart galaxies, stars, and even atoms. The universe would end in a state of complete disintegration. Heat death is related to the Big Freeze, but emphasizes the thermodynamic aspect. Over time, the universe will reach a state of maximum entropy. Energy will be evenly distributed, and no useful work can be done, leading to a state of eternal equilibrium. Vacuum decay is another intriguing scenario. This involves the universe transitioning to a lower energy state. Such a transition could occur if a bubble of true vacuum forms and expands at the speed of light, fundamentally altering the nature of the universe. Another possibility is the cyclic model. This theory suggests that the universe undergoes endless cycles of Big Bangs and Big Crunches. After each collapse, a new universe is born, potentially with different physical properties. The multiverse hypothesis offers a different perspective. It proposes that our universe is just one of many in a vast multiverse. Each universe could have different laws of physics, and the end of one universe might mean the beginning of another. In the our future, black holes will dominate the universe over incredibly long time scales. Black holes will evaporate through Hawking radiation. This process will leave behind a dilute gas of fundamental particles. As the universe ages, proton decay could play a role. Some theories suggest that protons might eventually decay into lighter particles. If this happens, all matter will disintegrate, contributing to the universe's ultimate demise. Dark matter and dark energy also influence these scenarios. Understanding their properties is crucial for predicting the universe's fate. Observations and theoretical work see Antonu to explore how these mysterious components affect cosmic evolution. The concept of a false vacuum adds another layer of complexity. If the universe is currently in a false vacuum state, it could tunnel to a true vacuum state. This transition would have dramatic consequences for the structure and laws of the universe. The cosmic landscape theory explores a vast array of possible vacuum states. Our universe might be just one region in a larger landscape. The transitions between different states could lead to the creation and destruction of multiple universes. Entropy plays a central role in many end-of-universe scenarios. As entropy increases, the universe moves towards a state of disorder. This principle underlies concepts like heat death and influences the long-term behavior of cosmic systems. Quantum mechanics also introduces uncertainty into predictions. Quantum fluctuations and the behavior of fundamental particles can lead to unexpected outcomes. These quantum effects might influence the ultimate fate of the universe. Exploring possible end of universe scenarios helps scientists understand fundamental physical laws. Each theory provides insights into the nature of space-time, and Matt R. The quest to understand the universe's fate continues to inspire and challenge our understanding of the cosmos. We've journeyed through the vast history of the universe, exploring its origins and evolution from the Big Bang to the present day. We've seen how fundamental forces shaped the cosmos and led to the formation of matter stars and galaxies. Our exploration took us through the early universe's chaotic beginnings, the birth of the first particles, and the subsequent separation of fundamental forces that set the stage for all cosmic events to follow. We delved into the creation of matter and the emergence of hydrogen and helium, the simplest elements that make up most of the universe. This process set the stage for the formation of the first atoms, and the cosmic microwave background radiation, a crucial relic from the early universe that provides insights into its initial conditions. We also examined how dark matter played a role in the universe's transparency and structure. The birth of stars and galaxies marked a significant milestone in cosmic evolution. We discussed the formation of population, 3 stars, the first luminous objects, and how their life cycles and supernova enrich the universe with heavy elements. These elements became the building blocks for planets and life, leading to the formation of galaxies and larger cosmic structures like clusters and superclusters. We also explored the intricate dance of galaxies, their interactions, and the formation of the cosmic web. This vast network of galaxies and dark matter filaments defines the large-scale structure of the universe. The role of supermassive black holes in galactic evolution and their influence on star formation and galactic dynamics were also key topics. The life cycle of stars from their formation in stellar nurseries to their eventual demise as white dwarfs, neutron stars, or black holes, highlights the dynamic processes that drive cosmic evolution. We looked at how stellar processes contribute to the creation of heavy elements and the ongoing cycle of star formation and destruction. Our focus then shifted to the formation of the solar system, the birth of the sun, and the accretion of planets. This process transformed a protoplanetary disk of gas and dust into a complex system of planets, moons, and other celestial bodies. The emergence of a habitable environment on Earth and the conditions that allowed life to flourish were pivotal points in this narrative. We also examined early human understanding of the cosmos, from ancient star gazes to the scientific revolution brought about by the CERNic model. This historical perspective set the stage for the development of modern astronomy and astrophysics fields that have profoundly expanded our knowledge of the universe. Modern astrophysics, with its advanced tools and techniques, continues to unravel the mysteries of the cosmos. The discovery of dark energy and its role in cosmic acceleration, the study of exoplanets, and the exploration of black holes and neutron stars are just a few of the many exciting areas of research. These studies have transformed our understanding of the universe and opened new avenues for discovery. We considered possible scenarios for the end of the universe, from the big freeze and heat death to the big crunch and big rip. Each scenario offers a unique perspective on the ultimate fate of the cosmos, highlighting the interplay between dark energy, dark matter, and the fundamental forces that govern the universe's evolution. And finally, we discussed the importance of exploring the universe From early observations to modern space missions, this quest for knowledge drives technological advancements and fosters international collaboration, pushing the boundaries of what we know and inspiring future generations. If you enjoyed this deep dive into the history and future of the universe, please like and subscribe to our channel. Don't forget to check out our other videos for more fascinating insights into the cosmos. Thank you for watching, and we look forward to exploring more with you in our next video.